On the auspices of this occasion, may I take the opportunity to extend a warm welcome to our most dynamic Chief Guest, Dr. Ashok Kumar Mishra, Professor of IIT Madras. Sir, may I request you to please take the dais. We have with us today our Chief Patron, Bishop, Diocese of Cuttack, CNI. He is the President JB of Stuart Science College, most esteemed Right Reverend Surendra Kumar Nanda. We welcome you, sir, to the dais. Next, our Honorable Secretary GB, Mr. Samarendra Pramanik, is requested to be seated on the dais. Now, our Honorable Principal, Dr. Deepa Nag, and our respected Head of the Department, Dr. Abani Kumar Sahu, and a dedicated Organizing Secretary.
It is said that flowers are the sweetest creation God ever made and forgot to put a soul into. To honor our esteemed guest with a symbol of love, respect and a warm welcome, we would like to invite our volunteers to come forward and present a bouquet.
May I request Ankita Sahu kindly do the honor and present the bouquet to our Chief Guest, Dr. Ashok Kumar Mishra. Thank you, Ankita. Thank you so much. May I request Richa Das to kindly do the honor and present bouquet to our Chief Patron, Bishop Right Reverend Surendra Kumar Nanda. Thank you, Richa. May I request Swarnamai Pradhan to kindly do the honor and present the bouquet to our Secretary GB, Samarendra Pramanik, sir. May I request Mitali Mohanty to kindly do the honor and present the bouquet to our Principal, Dr. Deepa Nag. Thank you, Mitali. May I request Stuti Padma to kindly do the honor and present bouquet to our Head of the Department, Dr. Abani Kumar Sahu, as a token of our heartfelt appreciation. Thank you. Prayer is the voice of the innermost heart. To start the event on a spiritual note, let's now welcome our Honorable Bishop, Right Reverend Surendra Kumar Nanda, for a soulful invocation.
We are very much thankful to God that God has given this wonderful opportunity to organize the international seminar, especially on current advances in optical spectroscopy and its application. So let us inaugurate it by prayer. So I request you all to stand and we'll have a word of prayer. Let us pray. Almighty God, most merciful Father, our Creator, our Sustainer, our Redeemer, we thank you, we praise you for this institution, the Stuart Science College. under the management of Diocese of Cuttack, Church of North India. Lord, you are only the God, and you have created us in your own image, and you have given us wisdom. You are the source of wisdom. And through that wisdom, we are surviving this world, and this science is one of that wisdom. Lord, chemistry is a subject through which we are able to benefit a lot of benefited through this. Today, we are having this international seminar in our PG Department of Chemistry, Stuart Science College. Lord, we seek your blessings, we seek your wisdom and knowledge so that this chemistry can help our society, our human being to develop their scientifically and physically. Everybody can be leading a sound life. Lord, we thank you. From the beginning of this seminar, let your presence be here, and we pray for our chief guest, pray for all the guests, be with them and those who are going to, Lord, lead the seminar. Lord, bless them richly, abundantly, so that let this seminar will be a successful one. We pray for our principal, Dr. Dipana, and also we pray for especially the Abani Kumar Sahu, Dr. Abani Kumar Sahu. Lord, bless them also. And also our chief guest, Padma Shri Professor Dr. Ashok Kumar Mahapatra. Lord, bless each and every person. Bless the student, bless the college, and bless this seminar. In Jesus' precious name we ask. Amen. Please be seated. Thank you so much.
Thank you, sir, for your prayers. It truly brought a sense of peace and clarity to this gathering. Now, I humbly request our head of the department, Dr. Abani Kumar Sahu, on stage for a condolence prayer for Professor Balram Sahu.
We gather today from across the globe, united by our shared passion for chemistry. It is with a profound and heavy heart that I must begin these proceedings, not only as the organizing secretary, but as a voice of our collective grief. Today, our seminar is cast under the shadow of a great loss. We are here without the guiding light, the inspiring presence of Professor Dr. Balaram Sahu, Professor of IIT Kharagpur. He is a cruel irony and a deep wound that the very person who was the soul of this initiative, who was present in the national seminar we organized previous year, the one who always inspired us to organizing an international seminar of this very nature, is not here to witness its fruition. Professor Sahu was not merely a colleague, he was a visionary. He was famous worldwide for coordination chemistry, which was published in world famous journal called Nature. He was the uranium scientist and a very established researcher. He passed away at the age of 94 due to cardiac arrest on 11th September 2025. In order to pay our tribute to the departed soul, I would request all to stand for 1 minute and pray for his soul to rest in peace. Thank you all.
Trees and plants are the nature's beauty and enrich our life force. I request to all our respected dignitaries to gather near the sapling and water the plant. This would demonstrate the noble deed with a mission. Big things often have small beginnings. Thank you everyone for your cooperation. Before we dive into the heart of today's seminar, we present before you a soulful opening song, Bande Utkala Janani. May I now invite our college chorus group to come forward and fill this space with their melodious voice. May I request to all of you please stand up for the Bande Utkala Janani song. Thank you.
शरीरा भारतमाळ सुशोभित तीरा भूतपयोधि विधौत शरीरा भारतमाळ सुशोभित तीरा शुभ्रतटिनी कुरशिखर समीरा जननी 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 वन्दे उत्कल जननी वन्दे उत्कल जननी गीता नीरभूधर माला साज तरंगे घन घन वन भूमि आजिता नीरभूधर माला साज तरंगे कर कर मुखरित चारु विहंगे जननी 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 वन्दे उत्कल जननी वन्दे उत्कल जननी चारु भासमयि चारु भासमयि चारु भासमयि चारु भासमयि जननी 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 वन्दे उत्कल 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 जननी
Thank you everyone. That was indeed a wonderful way to begin the day. To begin the meet and render a welcome address, I would like to invite our Honorable Principal, Dr. Deepa Nag, to welcome the audience.
Esteemed Chief Guest, Professor Dr. Ashok Kumar Mishra, Esteemed Chief Patron, Bishop Right Reverend Surendra Kumar Nanda, Esteemed Patron, Advocate Mr. B.D. Das and Mr. Samarendra Pramanik, Respected Organizing Secretary Dr. Abani Kumar Sahu, Eminent Keynote Speakers, distinguished delegates, honored faculty members, dear participants and students. A very warm and sincere good morning to each and every one of you. With immense pleasure and a profound sense of privilege, I extend a heartfelt welcome to this international seminar on current advances in optical spectroscopy and its applications. On behalf of the entire organizing committee and Stuart Science College, I thank you all for carving out time from your demanding schedules to be with us today. We are gathered here for the next 2 days to delve into one of the most dynamic and transformative fields of scientific inquiry, that is optical spectroscopy, which is the driving force behind revolutions in physics, biomedical diagnostics, material science, environmental monitoring, pharmaceutical development, and quantum technologies. This seminar is designed to be a melting pot of ideas. We are truly fortunate to have with us a galaxy of eminent scientists, researchers, and participants joining us from across the globe. I would like to take this moment to express my deep gratitude to our chief guest, Professor Dr. Ashok Kumar Mishra of IIT Madras, for gracing this occasion and inspiring us with your insights. To our chief patron, Right Reverend Surendra Kumar Nanda, your vision and guidance have always been a driving force behind our academics endeavors, and we are truly honored to have you with us on this significant occasion. To our patrons, Advocate Mr. B.D. Das and Mr. Samarendra Pramanik, your gracious presence on this occasion adds great value and dignity to this monumental event. We are deeply grateful for your constant support, encouragement, and visionary guidance, which have been instrumental in making this academic endeavor a reality. To our organizing secretary, Dr. Abani Kumar Sahu, your dedicated efforts, meticulous planning, and tireless commitment have been the backbone of this international seminar. To our distinguished keynote plenary speakers and invited speakers for agreeing to share your cutting-edge work. To our organizing committee, teaching and non-teaching staff, and the countless volunteers whose dedication and hard work behind the scenes have been invaluable. To our sponsors and partners whose generous support has made this gathering possible. Finally, to all the participants, you are the lifeblood of this seminar. My team and I are here to ensure you have a productive and memorable experience. In conclusion, let us not just be passive attendee, but active contribution. I wish I wish all a very stimulating and successful seminar.
Thank you, ma'am, for your inspiring words and setting the perfect tone for this seminar. Now we come to the time when we would be felicitating our guest. Firstly, we would like to felicitate our honorable chief guest of this event, Dr. Ashok Kumar Mishra. To honor the dynamic and dazzling personality, may I request Bishop Right Reverend Surendra Kumar Nanda to please help us present the memento. It is indeed a great honor and privilege to have a great personality like Professor Dr. Ashok Kumar Mishra. He completed his BSc Honours from DAV College Titlagar, MSc from University of Delhi, and received PhD from IIT Kanpur in 1985. After a stint in Sambalpur University as a faculty member from 1984 to 1992 and in Gumna University, Japan as a Monbusho Fellow. He joined IIT Madras in 1992. He is currently the President of Indian Photobiology Society. He received Bronze Medal from the Chemical Research Society of India and Fellow of the National Academy of Sciences, India. He has also received Acharya P.C. Rai Memorial Award from Indian Chemical Society and Professor V.U. Malik Memorial Award from the Council of Chemists. He has an active research group so far. He has guided 35 PhDs, many MSc students, and published about 235 research papers. Time will fall short, sir, if I talk in detail about your personality and contribution. Thank you so much, sir. We are truly honored by your presence and your gentle gesture.
Next, we would go ahead to pay our respect to the Honorable Bishop Right Reverend Surendra Kumar Nanda. To do the honor, may I request our principal, Dr. Deepa Nag, and Secretary GB, Mr. Samarendra Pramanik, to please help us present the memento. Sir is the chief patron of this two-day event. He is the Bishop of Diocese of Cuttack Sienai and President of our college. He completed his Master in Arts from the Berhampur University, obtained his Bachelor of Divinity on the year 1992 from the Senate of Serampur College, Bangalore, under the Senate of Serampur University. He has joined Associate Presbyter at English Baptist Church, Sienai, Cuttack, of the Diocese of Cuttack Sienai in the year 1992. Sir always holds a high position in our heart with a humble gesture and spiritual intensity. We thank you, sir, from the core of our heart for being present among us despite your busy schedule. Next, we are proud to extend our felicitation to Mr. Samarendra Pramanik, sir. Sir is the secretary of the governing body of our college and the Diocese of Cuttack Sienai. To do the honor, may I request our principal, Dr. Deepa Nag, and head of the department, Dr. Abani Kumar Sahu, to please help us pay our acknowledgement. Sir has been present physically and mentally amid us since the conception of this conference. He is our guiding light in every small and big aspect of processing of our college. All the decision making related not only to the event but in all the academic as well as administrative aspects of the college. Sir has remained a strong pillar behind us all. Thank you so much, sir, to be there with us and give inspiration and confidence whenever we are in need.
Let's now move forward for the next felicitation of the day. Our respected Principal Dr. Deepa Nag. To do the honor, may I request our Secretary GB, Mr. Samarendra Pramanik, to please help us to present the memento. On focusing our respected and most dynamic, I would rather say the Iron Lady who stands like a pillar to support the entire event, without whom it would have been incomplete. It is our privilege that she belongs to our chemistry department and holds the responsibility of functioning and managing our college and all its activities with great care, determination, and devotion. We are deeply grateful for your unwavering support, your commitment to academic excellence, and your belief in creating platforms like this that connect global knowledge with local aspiration.
As we near the end of this felicitation program, it is time to honor our head of the department, Dr. Abani Kumar Sahu. To do the honor, may I request our Secretary GB, Samarendra Pramanik sir, to please help us present the memento. Dr. Abani Kumar Sahu is not only the head of the department, but also the backbone of our department. He is the guiding and driving force of our department, whose constant encouragement, mentorship have been instrumental in every success we celebrate today. Thank you, sir, for your dedication and tireless efforts. It motivates us to do better every day.
It's now time for one of the most awaited moments of today's seminar. A souvenir is not just a collection of pages. It is the vibrant reflection of our academic journey, students' contribution, faculty excellence, and creative spirit of chemistry department. May I request our esteemed dignitaries to kindly come forward for the unveiling of the souvenir. and I request our volunteers to come to the dais to help us unveil the souvenir. We extend our heartfelt thanks to everyone who contributed to making of this beautiful souvenir. Let it be a reminder of today and an inspiration for tomorrow.
May I now respectfully invite our Honorable Secretary GB, Mr. Samarendra Pramanik sir, to address the gathering.
Thank you. Honorable Chief Guest, Professor Ashok Kumar Mishra, honored guest from abroad, Professor Haruka Hashoi, revered Bishop Right Reverend Surendra Kumar Nanda, President, Governing Body, and Chief Patron, Stuart Science College, Cuttack, respected Principal Dr. Mrs. Deepa Nag, former CEO Advocate B.D. Das, distinguished guests on the stage and off the stage, participants and members of faculty, Stuart Science College. It is my distinct pleasure to welcome each one of you for the inauguration of the International Seminar on Current Advances in Optical Spectroscopy and its Applications. I am truly thrilled to witness such an enthusiastic gathering of science students, all here to discover the fascinating world of science. Science plays a crucial role in shaping our present and future, drawing innovations and improving the quality of life. This seminar provides a vital platform for young minds to share their scientific ideas, develop their skills in expression and presentation, and be inspired to pursue careers in science. I am confident that this event will serve as a beacon, illuminating new paths in scientific understanding, sparking conversation that will lead to groundbreaking discoveries. The dedication of the organizing committee, The expertise of our speakers and eager participation of all of you are the cornerstones of our success and impactful seminar. I extend my sincere gratitude to everyone involved in making this seminar a reality. To our distinguished guests, thank you for gracing us with your presence. To our young participants, I urge you to engage and explore with curiosity and an open mind. I wish you all a day filled with insightful discussion, valuable learning experience, and lasting impressions. Thank you.
Thank you, sir. Your vision always inspires us to aim higher and do better. May I now humbly invite our chief guest, Professor Dr. Ashok Kumar Mishra, to address the gathering and share your valuable insights with us.
So, honorable dignitaries on the dais and dignitaries off the dais. As all of you know, Professor Ashok Kumar Mahapatra is supposed to be the chief guest. He could not come. I'm just filling in the slot. So the filling will not be that proper. So I'll just sort of tell a little bit of what I felt about this conference. What really surprised me, and I admire, that look at this, an international conference, and online you got so many speakers from all over the world, and I saw the titles of the talks also and so on. Excellent talks. The choice of speakers are good, and so I think this is the first time I'm seeing in Odisha that there are so many online talks that are going to come from various parts of the world. And it's not like Indians settled abroad kind of a thing. There are truly non-Indian scientists who are going, quite a few of them that are going to come. And we are really fortunate and lucky that Professor Hosoi from Japan has physically come here. I'm sure, I mean, she's one of those leading biological spectroscopists in a sense in Japan as well as in the world. So very recently she was in another conference in Goa, and that facilitated her for coming easily from Goa to here. From here she will be going to Delhi, and then she will be going to Kanpur, IIT Kanpur, and many other places she will be going around, and after that she will go back. So thank you, Professor Hosoi, for agreeing to our invitation and coming. So this is my general feeling. Like I said, I'll be giving a regular keynote address later after this is over, and that keynote address will be mostly for the students. So hopefully by then the students will be here in the audience. That's all I have to say. I congratulate the college for, this college is very, very old, as you know, you have already been told about it, roughly 80 years old, very distinguished college. The teachers are one of the best group of teachers that you always find here, and that reflects on the output from here. A very large number of students from here are in very good positions everywhere. So I'm sure the college will continue maintaining its the admirable service that it is going to the, for the students and all. So all my best wishes for this conference as well as for the college. My special thanks to Professor Avani Babu, the kind of passion and intensity with which he has pursued organization of this particular one. I marvel at. Thank you all. Thank you very much.
Thank you so much, sir. Your thoughts have truly enriched the seminar. And with great respect, now I invite our esteemed organizing secretary and head of the department, Dr. Abani Kumar Shau, to share a few words and address the gathering.
Good morning, everybody. Honorable distinguished chief guest, Professor Dr. Ashok Kumar Mishra, esteemed chief patron, Bishop Right Reverend Surendra Kumar Nanda, esteemed patron, Advocate Mr. Vibhudatta Das and Mr. Samarendra Pramanik, esteemed convener and principal, Dr. Mistress Deepanag, eminent speakers, delegates, and media persons, respected colleagues, and dear participants and loving students. It is my immense pleasure and a singular honor on behalf of the organizing committee to extend a heartfelt welcome to this international seminar on current advances in optical spectroscopy and its applications, which is a dream that comes true today. First and foremost, I extend my heartfelt thanks to the Almighty God. We are truly thrilled and humbled to see the gathering of brilliant minds from all over the world. Your presence here today in person and some joining us virtually is a testament to the vibrant and dynamic nature of the field. Strong vote of confidence in the goal of this seminar. The journey to this day began many months ago, fueled by a simple yet powerful idea to create a premier platform where scientists, researchers, and industry experts can coverage to share, discuss, and debate the groundbreaking innovations shaping the future of optical spectroscopy. From ultra-fast laser spectroscopy to novel biomedical application, from single molecule sensing to advanced material characterization, our aim is to traverse the entire exciting landscape of the discipline. The theme of the seminar, Current Advances in Optical Spectroscopy and its Application, explores the cutting-edge innovation that are pushing the boundaries of the field, focusing on the development of ultra-sensitive, high-resolution, and ultra-fast technique like single-molecule spectroscopy, nano-optics, and multidimensional methods. This theme highlights the pivotal role of optical spectroscopy as a driving force for scientific discovery and technological progress by bridging fundamental research with real-world solutions. Organizing an event of this scale is a monumental task, and it would not have been possible without the collective effort of many. At first, it is my pleasure, immense pleasure and honor to extend a very warm welcome to our distinguished chief guest, Professor Dr. Ashok Kumar Mishra. Professor Mishra is currently the President of Indian Photobiology Society and a Professor Emeritus in the Department of Chemistry, IIT Madras. Sir, your presence here today is a great source of inspiration for all of us and adds significant prestige to this event. Your incredible contribution has truly elevated the experience for everyone involved. It made the event feel more cohesive and insightful, especially given our diverse international audience. Thank you again, Professor Mishra, for your generosity and for sharing our expertise so willingly. It is a great pleasure to work with you. Thank you, sir. Thank you. I would like to take this moment to offer my sincere gratitude to Chief Patron, Bishop Right Reverend Surendra Kumar Nanda, sir. Sir, your gracious presence and unwavering support are the bedrock of this event. We are deeply grateful for the guidance and encouragement you have provided us, which has made this international seminar possible. I extend my heartfelt gratitude to the patron, Advocate Vibhudatta Das, for instilling in me to the confidence to address all of you. Sir, your support for this seminar has been both foundational and transformative. Your invaluable technical guidance has ensured its quality and intellectual depth. You have not only enabled this event, but have actively shaped in success. On behalf of the entire organizing committee and all participants, we offer our deepest gratitude for your visionary partnership, your belief in our mission in both an honor as an inspiration. Thank you, sir. I would like to express my heartfelt gratitude to our patron leader and mentor, Mr. Samarendra Pramanik, Secretary GB, Stuart Science College, for his unwavering enthusiasm and dedication to the college growth. His constant drive has enabled us to realize our aim of organizing the seminar on such a large scale. I would next like to acknowledge the convener of the seminar, Dr. Deepa Nag, Principal, Stuart Science College, for her relentless effort in making this dream of international seminar a reality. Thank you, madam. I would like to express our deepest gratitude to our keynote and invited speakers, Professor Dr. Ashok Kumar Mishra, Professor Dr. Haru Kohosoi, Professor Sumanto Kumar Padhi, Professor Sudhanshu Shekhar Tripathi, Professor Himanshu Shekhar Biswal, Professor Hare Krishna Sahu, Professor Saugata Sahu, Professor Digambar Patra, Professor G.C. Nayak, Professor Karatijina Gach Janchek, Professor William Mogino Fidijo, Professor Dr. Lekha Pramanik, Professor Dr. Evelina Gerogiva, Professor Dr. Stephen Bellamy Lopanaj, Professor Jagannath Panda, Professor Jaidev Dinda, Professor Bankim Chandra Tripathi, Professor Vikas Kumar Jana, Professor Vijay Lakshmi Jana, Professor Punnendu Padi, Professor Ratan Kumar De, Mr. Balogun Ayo Felix, Mr. Bernard Anagonum. Thank you for accepting our invitation and for agreeing to share your pioneering work and invaluable insight with us. You are the cornerstone of this seminar. Along our distinguished speaker, we have an impressive lineup of emerging researchers and graduate students who will share our discoveries and perspectives. I urge everyone to interact with these new scholars and provide them with support as they symbolize the oncoming generation of innovators and intellectual leaders in the discipline. It is with immense pleasure and a touch of personal privilege that I extend a very special welcome to our distinguished professor, Dr. Satyavan Jena and Professor Sudhanshu Tripathi. Professor Jena and Professor Tripathi are not only a renowned authority in the field of chemistry, but for me personally, they are the teacher who laid the very foundation of my own journey in this subject. Thank you, sir. They are the teacher who laid the very foundation of my own journey in this subject. Thank you, sir, for being here with us today. Again, thank you. I want to recognize the dedicated work for every member of the organizing committee, the technical support team, chemistry family members, all my colleagues of the office and volunteers who have invested countless hours in planning, coordinating and assembling every small detail to make this seminar a reality. Your dedication to excellence in what has made today possible. I would also like to express my sincere gratitude and support to your sponsors and partners for their dedication to promoting scientific progress. Your participation is crucial in determining the direction of the seminar. Thank you. There is a special honor and a profound personal privilege reserved for this moment in our proceedings. It is my distinct pleasure and indeed one of the chief joys of my role as a organizing secretary to rise and extend a most heartfelt welcome to a giant in the field of chemistry and a person to whom I owe an immeasurable debt of gratitude, to my teacher, Professor Dr. Prabhat Kumar Mishra sir. On behalf of the entire organizing committee and every life you have touched, a very warm welcome to you, sir. We would like to felicitate you, sir. I would like everyone to shift some focus on the pioneers of the department. I would like everyone to shift some focus to the pioneers of the department, as this department would not have thrived as it today without them. I am grateful to all the past members of the department who dedicated their valuable time to be with us. I would now like each of you to come up to the dais, individual to receive a small token of affection and recognition from us from a form of appreciation. Sit. First, I would like to call upon stage the senior most former head of our department and a dynamic person, Dr. R.K. Satpathy sir. Dr. Satpathy was the head of the department from 1st January 1990 to 30th September 2000. Dr. Satpathy taught chemistry in degree level for 39 years and retired as reader and head of the department in the year 2000. Thank you, sir. It is with immense pleasure and deep respect that I extend a heartfelt welcome to our next former head of the department, Dr. Girish Chandra Mishra, to please come up on the dais and honor us by receiving felicitation. Dr. Mishra was the head from 23rd April 2021 to 31st December 2006. Thank you, sir. I would now request Dr. N.K. Karo to please come up. We are really honored to have you here today, sir. Dr. Karo was the department head from 1st January 2007 to 31st August 2011. Sir, please. Thank you, sir. I would now like to invite Dr. N.C. Pati to share the stage. Dr. Pati made a significant contribution to the department's well-being and efficiency. Under his active academic supervision, the department transformed its form and framework. My profound appreciation will always be with Dr. Pati. Thank you. Next, I am honored to have our proceedings head, Dr. S.P. Bhattacharya among us today. Dr. Bhattacharya was the department head from September 1st, 2011 till February 28, 2015. Sir, thank you so much for graciously accepting our invitation. Thank you, sir. Further, I request our former principal, Dr. Devashish Pradhan, to join us. We are really blessed to have him with us here today. His contribution not only to the department but to our college is spellbound and glorious. Thank you so much, sir, for appreciating our invitation. Absent. Now I have a peculiar exhilaration about calling my immediate former head of the department, Dr. Aparna Datta, to the stage. Dr. Datta was the head from November 1st, 2021 until February 29th, 2024. Dr. Datta's experience are still vivid in my mind despite having recently retired. Her academic prowess was left an imprint in the mind of every graduate of her program. Thank you, ma'am. On behalf of the organizing committee, it is my distinct pleasure to extend a very warm welcome to all the members of the Odisha Chemical Society. Today, as we gather in the international seminar to chart the future of chemistry, we are profoundly privileged to be in the presence of a few such giants, architects of modern chemistry, whose contributions have not only advanced science but have fundamentally uplifted the entire field. Your shared passion for advancing the field of optical spectroscopy is what brings true meaning to this gathering. We are thrilled to provide this platform for you to connect, share groundbreaking research, and foster collaboration that will shape the future of chemistry. On behalf of the organizing committee and very participants here, it is my immense honor to extend a heartfelt and celebratory welcome to our distinguished cohort of chemists who have, through their brilliance, perseverance, vision, reshaped our understanding of the molecular world. First, Madam Professor Subhasini Lenka, please come. Thank you, ma'am. Professor Dr. C.R. Mishra, sir. Professor Dr. Ajay Kumar Patnaik. Sir, thank you, sir. Professor Dr. Smruti Prabha Das. Professor Smruti Patnaik. Sir. Professor Siddharth Bharadwaj. student of Stuart Science College. Professor Asit Parija. Also student of Stuart Science College. Dr. Debidatta Das, head JKBK. Dr. Debashish Das, BJP College. हाँ BJP मानती. Dr. Debashish Mahanti, BJP College. Professor Subhash Chandra Sahu. Thank you. To summarize, encourage each of you in the audience to take advantage of these events, to participate actively in every conversation and contact, to indulge in questionnaire session and to challenge yourself to think differently in this bliss of information. Let us utilize this seminar as a springboard of new synergies, both formal and informal, as well the type of mutual enrichment that has always been at the corner of scientific development, and take advantage of this chance to learn information and establish network that will continue long after the seminar. Thank you and welcome you all again for being here. Let us illuminate this seminar with the same brilliance that spectroscopy brings to science. May the days ahead be filled with discovery, dialogue and dazzling insights. Thank you, thank you, thank you.
Thank you so much, sir. Your leadership continues to inspire both students and faculty alike, and your guidance is truly invaluable to all of us. And again, thank you so much to all the dignitaries. With that, we conclude the inaugural session of this prestigious international seminar, Caosa 2025. A heartfelt thank you to all the dignitaries for their inspiring words. But the journey has just begun, as we now step into the core of our seminar, the talk session. We are about to dive into the heart of knowledge, innovation, and international collaboration. And to guide us through this next segment with poise, it's time for us to take leave and my co-anchors to take on with the talk section. Thank you so much.
Thank you.
ବର୍ତ୍ତମାନ ସାର୍ ଅଛନ୍ତି ଚେୟାରପର୍ସନ୍ ଡାକିବ ଆଉ ଅଶୋକ ମିଶ୍ର ସାର୍ ଫାଷ୍ଟ ହେଲା ଆମେ ଆରମ୍ଭ କରୁ ସେମାନେ କହୁଥାଉ ସେମାନେ ଆରମ୍ଭ କରିବେ ଭେରି ଗୁଡ୍
Namaskar and a very good morning to all. Thank you once again to all our esteemed guests, delegates, and my co-anchors for making the inaugural session such a memorable and graceful start. Before we move on, let us introduce ourselves. I am Shruti Sambhavna, and joining me is my co-anchor, Pritika, both pursuing undergraduation from the Department of Chemistry. Together, we will be your hosts for today and will be guiding you through the proceedings of this seminar.
This year's focus is on optical spectroscopy, a science that uses light to uncover the secrets of matter. From molecules to materials, optical spectroscopy reveals details far beyond the reach of the naked eye. उधर ही तो है
I would request everyone to be please seated down so we can start the program. Start.
मैं थोड़ी बोलूँगी
फिर से स्टार्ट करेंगे.
गेस
No.
ठीक है दिस ईयर से हो गया सुन रहा है क्या आवाज़ कंटिन्यू बोलो को सुन ही नहीं रहा है
We may now start the program.
This year's focus is on optical spectroscopy, a science that uses light to uncover the secrets of matter. From molecules to materials, optical spectroscopy reveals details far beyond the reach of the naked eye. And today, through our speakers, we have the chance to see science illuminated in an entirely new way. We would now request our jury member for this session, Professor Satyaban Jaina, to come up on the stage.
बोलना पड़ा क्या करते हैं मतलब बोलना पड़ा उससे बात करना पड़ा कोई गाइड करके लेने आने वाला चाहिए
बैठ जाते हैं सर
बैठेंगे सर क्या हुआ पता नहीं
अकेले अजीब लगेगा क्या
नहीं दीदी लोग तो बैठे थे बट हम क्या करेंगे Without any further delay, let's dive into the speaker's session. It is my privilege to introduce you to our keynote speaker, Professor Dr. Ashok Kumar Mishra, a distinguished academician and a researcher. Professor Mishra is a professor emeritus of chemistry at IIT Madras, widely respected for his pioneering contributions to physical photochemistry and fluorescence spectroscopy. With an illustrious academic journey, Professor Mishra has served as a faculty member at Sambalpur University, a Monbusher Fellow, and JSP as visiting scientist at Gunma University, Japan, and later joined IIT Madras in 1992, where he went on to hold several key leadership positions, including head of SAIF and Dean of Academic Research. He has also been an active member of national and international committees such as SCRB IPC, DST FIST, SPIE Photonics West. A visionary leader in chemical sciences, Professor Mishra is currently the president of Indian Photobiology Society. His scientific excellence has been recognized with numerous prestigious awards, including the CRSI Bronze Medal, Acharya P.C. Rai Memorial Award, Professor W.U. Malik Memorial Award. He is also a Fellow of the National Academy of Sciences, India. With great anticipation, I invite Professor Dr. Ashok Kumar Mishra to share his insights on optical spectroscopy, probing the secrets of light-matter interaction. He will guide us through the principle, instrumentation, and remarkable insights gained from methods ranging from microwave to ultraviolet spectroscopy. Thank you.
যেটা ভালো হবে সেটা না না, ମୁଁ ଖାଲି ଠିଆ ହେଇକି କହିଲେ ଚାହୁଁଛି। I want all the students to come. Have the students come already? BSc, MSc students, please. We'll start now. Yes. So what attention please. So what I'll be doing is this. We'll start with very basic light and matter interaction. I don't have any slides. There is no big technical thing here. It's all like to give you a feel for what spectroscopy is. Okay, this feeling may help you in later. So first thing is light matter interaction. Spectroscopy is about light matter interaction anyway. So in this light matter interaction, please remember that the light that will be interacting with matter will be originating from matter, from atoms, from molecules. For example, gamma radiation comes from nucleus, very high energy. Right up to, go to radio waves, much longer, but they also come from material, right? Origin will be from matter all the time. So the light that comes from matter reflects the origin, the way the matter was designed already, or the construction of the matter, the whole thing. So what it happens is this. You already know that light is called electromagnetic wave. What it means is that there is a electric vector, electric component, and there is a magnetic component, and many of you know that they are orthogonal to each other in their orientation. And in light, they will be always in phase. And the node for the electric component wave and the node for magnetic component wave will always be the same. They are orthogonal to each other. And remember one more thing. The electric vector component will interact with materials atoms, molecules, everything together, differently, and the magnetic vector component will be interacting differently. And this much you know already to some extent, that for example, when you are talking about the magnetic vector component, you are talking about NMR, EPR, electroparamagnetic resonance, nuclear magnetic resonance. So you are making use of the magnetic vector component. What happens is when we say the title like optical spectroscopy, colloquially it means only electric vector component. The other one is called resonance spectroscopy. The irony is there is no spectroscopy without resonance anyway, whether it is electric vector or magnetic vector. Okay, so it's just language. Okay, optical spectroscopy in general is about the electric vector component interaction with matter, and resonance spectroscopy they call it is magnetic vector. Plus, don't be misled by that. Both are resonance, and both belong to the general big picture of optical spectroscopy because they are photons to be interacting. Okay, that is one. And the range you already know. The range is, it starts from picometer range into the minus 12 meter range for which one? For a photon that is coming out of nucleus. The energy gaps are much, much larger there. Any reorganization within the nucleus, the energy that is coming out or the energy that probably can go in will be in the gamma range. Extremely strong, extremely powerful, extremely energetic in its photon. From that range, you go up to 10 to the power plus 3 meters, kilometer range, right? So this entire range is electromagnetic wave. And what is the order of magnitude here? Plus 3 to minus 12 is 15 orders of magnitude change in the wavelengths and 15 orders of magnitude change in the corresponding frequencies. Each of these photons, as I said, as it comes out of material. If it goes to while coming out of the material, it is carrying some signal from material. When it gets absorbed by a material, it is telling us something about the material. Because what property of the matter is actually making this, either the electric component or magnetic component getting absorbed. Now, this is one way of looking at it, is the wave part of it, the wave nature of light. The other way is, the quantum nature of light, the photon nature of light. Light, as you know already, like you decide what you want to get from me, I will give you type of kind of a thing. You look me at as a wave, I will be a wave. You look me at a particle, I will be a particle. Photon, right? Now, what do you mean by looking at it? Any looking at, in that sense, is interaction. That means the interaction that you will have with light will tell you whether light is matter or a photon or a wave, right? All these interactions, any interaction you can think of, is always an energy exchange interaction. It has to be, including light scattering. Even if it is a, what they call, I forget that word right now. Oh, okay. So, any kind of scattering, including scattering to light absorption, interaction has to be there. Interaction has to be energetic. If you talk about these energies, understanding something, I can use sound to understand. I can use, gravitational energy to understand some matter, the way it falls and so on, something like that. I can use mechanical, energy, forces, etc., to understand a matter. I can do all that. But each of the other ones will require a lot of energy exchange. With a photon, the energy exchange can be minimal, giving you a lot of information. What I mean to say is, if we try to understand the material universe, light matter interaction is a must. Understanding that, spectroscopy is a must. Spectroscopy covers the entire dynamics, entire aspect. There is another property of light. It is not just the energy part of it, or the wavelength part of it, or whatever. There is another important property of light that is called polarization. Right? if you polarize if single photon that is coming out of matter is by definition polarized. When you say unpolarized light, you are talking about a very large number of photons, probably Avogadro number of photons, which are all oriented in different polarization. You are seeing the end result of that. A photon by itself is always polarized, right? And what you can do then is to create your devices in such a way that you can get these bunches of photon to be having a particular orientation of polarization. Instrumentation is necessary for that, and so on. So that means you are not only using light, the energy property part of the light, for understanding this interaction, the orientation of the electric vector and correspondingly the magnetic vector is also playing and very important in the interactions that can happen or does happen. These two are important. This is called polarization properties. So these two are again extremely important to understand light matter interaction, to understand the corresponding spectroscopy. So what you already, this much I already explained that NMR, EPN, one type of spectroscopy is actually resonance spectroscopy. What it means by resonance is that for the energy to be transferred from light to matter or matter to light, they should be in phase. Energy gas must be same, the corresponding waves must be in phase. If not, there is no resonance energy transfer. Other than that, what can happen is scattering. Light comes, interacts and gets away. If it is an elastic scattering, that word I was forgetting right now. If it is an elastic scattering, the light comes and gets back with its own energy. The Rayleigh kind of scattering, right? Often what happens is the scattering is not always elastic. There can be inelasticity. Nothing is always ideal. Things are not always ideal. There are certain conditions by which the scattering will be inelastic. What it will mean is a little extra energy from material will enter into light. Little extra energy from light may enter into the material. The light will be losing or gaining a little bit of energy. What is that known as? Raman spectroscopy. Okay. And all the spectroscopies are extremely reliable, extremely important. But as on today, an analytical chemist looking at the nature of the leaf, whether the leaf is getting degraded or something like that, any instrumental analytical method, the simplest and the easiest way right now is a portable Raman spectrometer everywhere. That's because, why? If you are using resonance as a condition to understand matter, you have to have the particular wavelength of light, particular energy of light, which will be interacting with a particular property of the molecule and so on. What is Raman in a scattering, in inelastic scattering system, what will happen? We use any light, visible light, any light. These small changes that will happen will be happening in the different range, very, very different range, centimeter inverse ranges. Okay, because these changes will often talk about what is it called? There are two types of Raman, you already know this, a vibrational Raman and a rotational Raman. Rotational Raman line spacings will be much, much lesser in energy. You need a different detector for that. For vibration Raman, you need a different detector. But all these vibrations, the energy spacing of the vibration, the intensity of the vibration, tells a lot of information about the molecules from which it is coming. So as an analytical diagnostic device, right now, one of the best devices is Raman spectroscopy. And remember, that is also a part of spectroscopy because there is an energy exchange. Okay. If not, then what happens? If it is just a Rayleigh scattering, what happens? It gets scattered depending on the surface from which it is going. If it is just an atom or a molecule, the scattering will be sort of, depending on the orientation of the molecule, it will be on all directions. But if there is a surface, that scattering is what kind of scattering? For example, if I got a flat surface and light comes, no energy exchange, light bounces out, it will be reflection. These reflections, depending on the phase of the light, these reflections results in another line of another important area of chemistry. What is that then? How do you get the crystal structure then? XRD? Diffraction? Diffraction will happen when? This reflection wavelengths, right? They will be creating these diffraction patterns because of the overlap of the different waves, right? But that is a scattering based. The reflection is also a form of scattering because energy is not exchanged here. I'm trying to give you the big picture of light matter interaction, in which a part of it is spectroscopy. Are you able to get that to some extent? Some faces are very bright, looks like. Okay. But you can, later on, not in this mode, but we'll be there here, so you can ask later. So that is one. The other one is so resonance interaction I talked about, microwave, elastic, inelastic, and what else? You already know this, oscillating electric vector will go to a kind of spectroscopy which is colloquially called optical, and oscillating magnetic vector will give you resonance spectroscopy, they call it, but both are optical. And that is. Now the other one is, what is the range through which you can use these spectroscopies? As I said, you are starting with gamma rays, right up to kilometer long wavelengths. What you are looking at is, you can look at atoms, you can look at molecules, you can look at any arrangement of material. Right. So why it is possible that you can go over the entire dimensional range to understand them? Because light is coming from those dimensions anyway. And they will interact. That's important to understand. Now the other aspect of there, it is like this. So for example, if you get a peak, you take a spectrum, you get a line, you get a peak. The intensity of peak, the position of the peak at what wavelength it happens tells you something. What about the relative intensity of the peaks? For example, if you take a ultraviolet UV visible spectrum, for n pi star transition you get a smaller peak, smaller band. Pi pi star you get a larger band. Why it is so? It is so because the two energy states that are there, right? So how these two energy states interact with each other through light? Remember, these states in quantum, in any model of a molecule, you'll remember all the states are orthogonal to each other. That means there is no possible interaction between them unless you perturb one of the states. You make it non-orthogonal. And what makes the state non-orthogonal? Light. Got it? So you use a light operator on a function, modify it. The modified one is no more orthogonal to the other function. So then they will interact in presence of light during that time, which is femtoseconds. All right? Okay. So why I'm saying this is, if you understand these basic ideas, you will see, probably you will get a feel for spectroscopy a little better, other than just noting equations and remembering them and so on. That is important, otherwise you will not get a concrete number. You have to remember equations, you know how to manipulate, you know how to all the mathematical manipulation, other than you will never get a solution, get a number. But if you feel good about it, if you have understood what exactly you are doing in general. So that is the purpose of my telling all this. So as I said, light energy intensity property you are using, polarization property you are using, and all that. So that is all possible. And Raman has become, I forgot to tell, Raman has become such a powerful technique. You know why? All these scattering lights for Raman, that is inelastic scattering, intensities will always be small. Raman got a Nobel Prize, but application of Nobel Prize, Raman spectroscopy came only when laser came. You needed an intense laser beam so that small peaks can be large enough for a detector to detect. even today. And now the lasers have become much more very small, tiny devices. You can carry them everywhere and so on. Miniaturization is a big thing that is happening in current instrumentation almost everywhere. Sophistication is increasing very significantly. Okay, and it's growing. I don't know how far it will grow, but it's growing very fast now. So, etc. Then what else? I was coming to instrumentation. That is the last one, then we'll stop. Remember, we understand light matter interaction, but we'll be often limited while designing the instrument. Think about a UV visible spectrophotometer. When we were using it, we had to have a deuterium lamp, D2 lamp, which will be giving us some energy level at the ultraviolet to visible range, but not at a longer range. Then we'll have a tungsten halogen lamp in a different range. There will be overlap. The instrument designs will be a little not so good. You have to take care of all this overlap part and the sensitivity part and normalization part, a lot of those kind of things. Today, it has become very different. It is just a xenon lamp which will take care of it. But then, in UV visible spectroscopy, you know what you are doing? It's a ratiometric one, Beer-Lambert's law. Because it is ratiometric, as long as the detector is detecting to a certain level of acceptance, you are talking about the relative intensities. You don't need a powerful lamp. Anyway, you are going to divide one by another. You don't need a powerful lamp as long as the detector is sensitive enough. And they are collinear. UV visible, you know, the light comes, light goes, you see how much of light is lost on the reference side. Some light will be lost there through scattering. And how much of light is lost through the light absorbing medium size. Then you are comparing that I0 by I, etc., etc. And that works well there. But what about fluorescence? Someone of you have seen a fluorescence spectrophotometer? Ever read about it? No. Anyway, so in fluorescence, fluorescence comes from light that is already there in the molecule and it's coming out, right? So what happens in fluorescence then is, when the light comes out of matter, remember, it is not the same light that entered into the matter. The molecule, let us say, has taken the light and digested it. The electron has moved here and there. And after that, the photon that is coming out is vomiting out. So it is not the same light. But then there will be some correlation between these two lights with regard to some properties, quite a few properties, including polarization and all that. But they are not the same. It's not a scattering light which is the same light. Scattering light is always the same light. But this will be absorbed light getting emitted again, retaining some of the properties of the absorbed light. If I am going to look at fluorescence, then the fluorescent photon can come out in all directions, 360, all directions. Now if I am to collect fluorescent photons, I can get it from any direction. So then if the light is coming from one way, I don't look at fluorescence from this side. I will be losing out fluorescence intensity, which will be lesser with the light that is already passing through. The scattering light, the light that is going through it, that will be much more intense. The intense light will be actually swamping the fluorescence light to some extent. Then what do? I go for the least scattering mode, which is orthogonal to it, right angle to it. My fluorescence data will be a little more pure. A little bit of scattering will still be there, but it will be much more pure. But for fluorescence, again, I will be needing a higher powerful light, unlike the UV visible. All these design elements will have to go to any instrument that is used. For example, think about NMR spectroscopy. You create a magnetic field in which you are putting the molecule. You are using a radio frequency to be influencing the molecule under the influence of the magnetic field. which is orthogonal to the magnetic field. And you know where you are putting a detector? Again orthogonal to both of them. Understand? So all these regions, I mean, there is no time now for detailing all these regions. So you need to understand the light-matter interaction properly. Then only you can design instruments. Designing instruments will always be restrictive because of the availability of, for example, light sources and various elements that is already available to us. Detector sensitivities and so on. So what is big thing that is happening now is the basic spectroscopy that I talked about is there in all textbooks and all that. But people now keep on mixing them in such complex matter that the kind of spectroscopy that people can do today is very, very sophisticated. But the basics will be as they are. Spectroscopies are becoming much more involved and sophisticated, complex. The instrumentation is progressing very, very rapidly. Two things are happening. The precision is increasing, the size is decreasing, the cost is phenomenally increasing. We don't get easily in India. Okay, someday it will come, but by then it will be late. So this is the general condition now. Remember, without spectroscopy, we will never understand the universe. We are a material at all, not universe, anything around you also. Without spectroscopy, there is the lowest energy interaction method that will tell us with some of the biggest details of the analyte. Okay? There are other methods. There are many other methods which are designed for something which light cannot do. And that's a different thing. You can use ultrasound for many other techniques. Can you substitute ultrasound with light? No. And that's a different thing. But I'm not going into all that. Okay? So this is a general thing. I can stop here. Running out of my time. Whole idea is to get a feel. Okay. All my best wishes to all the students.
Thank.
If questions are there, if there is time for it, I'll be happy. Hello. Hello. But if there is no time, then we can stop.
Nobody is interested, any student, postgraduate students. But spectroscopy, you see, the most complicated topic. Say, if you don't understand anything, fine. If you understand everything, then you know chemistry. Okay?
Get a feel for it. Get a feel for it. That is important. Details are not necessary. Equations are not necessary.
He went to all the fundamentals of spectroscopy. Spectroscopy is the interaction of light with matter. That's all. But it appears the definition is simple, but the inner thing is very, very complicated. You have to understand each part of it. You interact. He is the expert in the area, expert in the subject. I mean, from Odisha, he is the best person in spectroscopy, if I am not incorrect.
No, there are much better persons coming up, I know.
Okay, anybody? Any student, at least one question? Yes.
Use a mic. Others should also hear.
Sir, you told that laser spectroscopy is essential to nowadays we can understand easily utilization of any molecular vibration concept and electronic transition. Is that easy to reliable, easily we can handle and judgmental any state of any particular material?
The laser expert is here, he can tell you. Himanshu here is, but what I can tell you is, the, yeah, I think he can give a better answer.
He has a lecture and you'll interact with him.
Yes, sir.
Here throughout.
Yes, sir.
What you are getting is much intense light, much properly controlled and oriented. That is the advantage of it.
Sir, exactly we are currently advances on that ultra-fast laser spectroscopy, so that it is range between femtosecond and picosecond. Is
The time dependence part I
Yes.
did not talk about. You can see attosecond is the ultimate limit.
So you told that that the laser
Femto onwards.
laser concepts literally apply after some interaction. Literally say that's why I.
No. There are steady state lasers.
Yes, sir.
Continuous light lasers.
Yes, sir.
Intensity becomes important,
Yes, sir.
and controlling polarization property is also very easy
Yes.
there in that. So those are advantages.
Yes, sir.
If you go to much lesser time scale, you cannot use a continuous beam. Energy consumption will be very high. You can only get a pulse of energy.
Methods, yes, sir.
And that is where you can go right up to femto.
Yes, sir.
Atto is difficult, femto possible.
Sir, one question, sir, is it affordable to that we can understand easily molecular material concept through ultra-fast laser spectroscopy? Is that handable to carry out, and it will be easily understood by us?
You can, what is not? Start with the basic spectroscopy, as I said.
Yes, sir.
Yeah, of course. Of course you can.
Yes, sir.
Sure.
Thank you, sir.
Okay, I will advise you first go through a book,
Yes, sir.
Pavia.
Palvia,
Very
yes, sir.
useful book, Pavia book.
Yes, sir, I'll go
For
through that.
molecular spectroscopy, you go through the book Banwell,
Yes, sir.
C.N. Banwell.
Yes, sir.
Very useful books to
Yes,
clear
sir.
your fundamentals.
Yes, sir.
Okay?
Yes, sir. Thank you. Thank you.
Okay, all the best.
So, if there is no other question, then let us give a big hand to Professor Ashok Mishra for the excellent lecture on the fundamentals of spectroscopy. On fundamentals of spectroscopy. Thank you. So, on behalf of the organizers,
Thank you, sir, for that enlightening presentation on optical spectroscopy. Your insights into the light-matter interactions and the advanced technique you highlighted have truly deepened our understanding. Now I would request Professor Ashok Kumar Mishra, Dr. Deepanag ma'am, and Dr. Bani Kumar Sahu to please come up on the stage and felicitate our jury, Professor Satyaban Jaina. Everyone, please join me once again in expressing a heartfelt appreciation with a big round of applause.
Next, it is our honor to welcome Professor Dr. Haruko Hosoe from the Department of Biomolecular Science, Toho University, Japan. Dr. Hosoe conducted postdoctoral research with Professor Yuichi Masuda on electron transfer in organic mixed valence compounds and later joined Riken under Professor Tahei Tahara, where she collaborated with Dr. Hideki Mizuno and Professor Atsushi Miyawaki to study fluorescence mechanisms of fluorescent proteins. Since 2006, she has led her own group at Toho University, focusing on elucidating fluorescence mechanisms as a foundation for developing novel fluorescent proteins. Her research uniquely integrates time-resolved fluorescence spectroscopy with molecular biology bridging physical chemistry and life sciences. Let us now hear Dr. Josue's talk on fluorescent proteins. Ma'am, please.
Pointer is showing, but since the LED is also flashing, so it is showing. But
weak.
Let me to speak.
Okay. I can.
You need that short.
Your time starts now. You can give a lecture for 40 minutes.
Yes. Okay. So may I start? Good morning. So I'm Haruko Hosoi, coming from Japan. Today I'm very happy to be here. And first of all, I'd like to thank Professor Abani and Ashok and everyone to give me this opportunity to talk about recent work. I'm from Japan, and this is my second visit to India, but this is my first visit here, so I'm very happy to be here. Today, I'm going to talk about fluorescent proteins. Green fluorescent protein, GFP, was firstly found from this jellyfish, Equoria victoria. It shows a green fluorescence. This is the structure of GFP. The chromophore is inside the beta barrel. Now, we have many colorful and functional fluorescent proteins, and using them, we can visualize living cells like these pictures. So fluorescent proteins, FPs, are widely used as essential optical markers in the field of molecular biology. So to use fluorescent proteins properly and to develop better fluorescent proteins, it is important to understand their fluorescence mechanisms. However, there are many different types of fluorescent proteins, and many of them are used without a sufficient knowledge of their fluorescence mechanism. So we are trying to find a generalized fluorescent mechanism of fluorescent proteins. In this regard, recently, we conducted these 3 studies. First one is about fluorescence lifetime, and the other 2 are about the dimerization of fluorescent proteins. So today, I'm very happy to share these results with you. So let's start from the first topic. In this study, we focused on 2 famous fluorescent proteins. One is EYFP, enhanced yellow fluorescent protein, and the other is EGFP, enhanced green fluorescent protein. These are the most common and used fluorescent proteins. And in this study, we clarify the unified role of the 145th residue on the fluorescence lifetime of fluorescent proteins from Equoria victoria. Enhanced yellow fluorescent protein is one of the most common fluorescent proteins from Equoria victoria. It shows yellow fluorescence. And interestingly, a single mutant, Y145W mutant, is non-fluorescent, like this. The difference is only tyrosine or tryptophan. So this residue is in direct contact with the chromophore. So in this study, the purpose of this study is to elucidate the role of the 145th residue. So we prepared EYFP and its 19 Y145 mutants and determined their fluorescence lifetimes using streak camera. And we performed these measurements, and this is the result of the time-resolved fluorescence decay curve. The black one the black one, longest one, is for the wild type, and the other colored ones are its Y145 mutants. As you can see, they are very different. And using that equation, we determine their fluorescence lifetimes. And we found that the lifetime is very different. For the wild type, the most light one, the lifetime is 3.1 nanosecond. And these alphabets indicate one letter code of amino acid. So that W means EYFP Y145W mutants. It has the shortest lifetime. And the variation in lifetime is very large. So we found that a single Y145 residue control their fluorescence ability. So we wondered what properties of amino acid are important. And we found that a good relationship between the fluorescence lifetime and the side chain volume of amino acids. These are the value of side chain volume of each amino acid. And when we plot the observed fluorescence lifetime against the side chain volume of the 145th residue, we found a good relationship between the lifetime and the side chain volume. For the wild type and the mutants with larger side chain volume have the longer fluorescence lifetime. And on the other hand, for the mutant with a smaller side chain volume have the shorter fluorescence lifetime. So we found that the role of the 145th residue is the steric effect. And we also found that these two are exceptions, including Y140W mutants. It is known that the twisting motion of the chromophore leads to a shorter lifetime. So this tyrosine is in direct contact with the chromophore. So for the wild type and the mutants with a larger side chain volume, the twisting motion is sterically hindered. Then it gives a longer fluorescence lifetime. And for the mutants with a smaller side chain volume, the twisting motion is not hindered. Then it gives the shorter fluorescence lifetime. This is the origin of the steric effect. So we felt good, and we wondered whether this finding is also available for other fluorescent proteins, and we examined EGFP, enhanced green fluorescent protein. The difference for EYFP and EGFP, the difference is only 5 amino acids out of 239. The most important difference is 203rd for EYFP, tyrosine, and for EGFP, threonine. The pi-pi stacking with the chromophore and the tyrosine changes the fluorescence color from green to yellow. So we examine whether EGFP Y145 mutants show the same steric effect. So we prepared EGFP and its 19 Y145 mutants and performed these measurements. And these are the results. That right one is the result for EGFP. Surprisingly, unexpectedly, the change is smaller for EGFP than that for EYFP. Accordingly, the change in the lifetime is also smaller for EGFP than that for EYFP. However, the volume dependence was observed even for EGFP. The wild type and for the wild type and the large mutants with a larger side chain volume have the longer fluorescence lifetime, and vice versa. But obviously, the slope is smaller for EGFP than for EYFP. So the volume dependence is smaller for EGFP than for EYFP. So this result was unhappy for us at that time. So we had to know the reason. So we compare the crystal structures. This red one is the superposition of YFP and GFP aligned by the chromophore. As you can see, two chromophores are well overlapped, and also the two tyrosines are also well overlapped. So the relative orientation of the chromophore and Y145 is essentially the same. It means the steric effect is essentially the same. So there must be another factor that reduces the steric effect. So we found that the hydrogen bonds around the chromophore are different between EGFP and EYFP due to the different two residues of 69 and 203. So for EYFP, there is only one hydrogen bond, and for EGFP, there are 4 hydrogen bonds. So the chromophore is more restricted for EGFP, and the restriction inhibits the twisting motion of the chromophore. So now we can understand the observed volume dependence as follows. For EGFP and EYFP, the steric effect is common and the most important factor. So in addition to the steric effect, hydrogen restriction by the hydrogen bonds partially suppresses the volume dependence, especially for EGFP. So we wondered whether this finding is also available for other fluorescent proteins. And we found good 2 cases. One is M-turquoise 2. So for M-turquoise 2, mutants with a smaller sidechain volume has a shorter fluorescence lifetime. This is an example YFP type. This is because the chromophore is hydrophobic and the restriction by hydrogen bond is less efficient. And the other case is sapphire GFP. These mutants with a smaller sidechain volume have the similar fluorescence lifetime compared to that of the wild type. So we conclude that the steric effect of the 145th residue is available for fluorescent proteins from Equoria victoria. So let me summarize the first topic. By the 145th mutation, the change in fluorescence lifetime is significant for EYFP and moderate for EGFP. And we found that the steric effect is the most important common factor. And in addition to the steric effect, the restriction by hydrogen bonds partially suppresses the steric effect. And we conclude that this finding is also available for other fluorescent proteins from Equoria victoria. So let's move on to the next 2 topics. In these studies, we focused on the dimerization of fluorescent proteins. The association of fluorescent proteins like this is very important to understand. This experiment is an example of the problematic imaging result. This top picture should be like the bottom one. It's completely different. For the top picture, the dimerization of 2 fluorescent proteins induces a change in the observed system. If we use a monomer fluorescent protein in the bottom, such dimerization does not occur, and it gives a proper result. So the association of fluorescent proteins sometimes gives a harmful effect. On the other hand, the association of fluorescent proteins is used for FRET-based sensor, in this case calcium ion sensor YC3.60. In the presence of calcium ions, the right one, FRET occurs in this dimer, and the fluorescence color changes from cyan in the absence of calcium ions to yellow in the presence of calcium ions. So the association property of fluorescent proteins is intensively utilized for the development of new fluorescent protein sensors. However, the dimerization behavior of fluorescent proteins is poorly understood. So we conducted these two studies about 3 fluorescent proteins from Escherichia bacteria. It is known that fluorescent proteins from Escherichia bacteria are likely to form dimers. So in these studies, we successfully elucidated the dimerization behavior of fluorescent proteins from Escherichia bacteria. To study dimerization, we performed time-resolved fluorescence anisotropy measurements. That one. Measurement, that right bottom one, is a typical result of this measurement. The change in the anisotropy reflects depolarization processes such as FRET. FRET occurs between these two subunits in a dimer, so we can detect the dimer formation using this method. So I want to start the second topic. In this study, we again focused on EYFP and EGFP. The dimerization behavior of these two fluorescent proteins is different. So we clarify the origin of the difference in this study. It is known that GFP and YFP have different dimerization tendencies. This is a result of OSER assay of a monomer fluorescent protein, EGFP and YFP. And when a monomer fluorescent protein is used, there are no structures inside the cell, indicating no aggregation. And the fraction of normal cells is about 100%. On the other hand, for YFP, there are many spots inside the cell, indicating the aggregation of YFP. The fraction of normal cell is around 40%. For EGFP, the number of spots is smaller than that for EYFP, so the fraction is around 80%. So YFP forms more dimers than EGFP. However, the intrinsic property of dimerization remains unclear. As I mentioned earlier, dimerization can be detected by FRET. This is the result of a transient absorption anisotropy measurement of YFP at a high concentration of 190 micromolar. The anisotropy changes from 0.40 to 0.28 with a time constant of 2.2 picosecond. This is due to homofret of EYFP between two subunits in a dimer. So we can detect the dimer formation using this method. And the value of 0.28, the anisotropy after FRET, is observed like this in our measurements. Because the time resolution of our steric camera is 20 picosecond, so FRET already completed at time 0. So this decay curve is reproduced by a single exponential function, and the R0, the initial anisotropy, is defined here. So the initial value here is very similar to that value 0.28. And at lower concentrations, the behavior is completely different. At 1 micromolar, this behavior is typical for a monomer fluorescent protein, indicating there is only monomers. And at 10 micromolar, the initial value decreases, indicating the dimer formation. As you can see, the initial value decreases at higher concentrations. So more dimers form at higher concentrations. So we perform the same measurements for EGFP and obtain these results. As you can see, the concentration dependence is smaller for EGFP than for EYFP. So the dimerization tendencies are different between EYFP and EGFP. So the FRET efficiency, energy transfer efficiency, is dependent on two factors. One is the distance R, the distance between a donor and an acceptor. So in this case, FRET occurs between two subunits in a dimer, like this. So the distance is constant. So the dimer fraction is important. When there are only monomers, this left one, the initial value is 0.4. And when there are only dimers, the right one, the initial value decreases depending on the dimer property. In this case, I gave 0.4 as an example. And when the fraction of monomer and dimer is both 50% for the middle one, the initial value is 0.3. So the initial value gives information about the dimer fraction. And the FRET efficiency is also dependent on kappa square, the orientation factor. That is the relative orientation of the donor and the acceptor. So the transition dipole moment of fluorescent proteins is like that. So even when there are only dimers, the initial value can be different by the different relative orientations. For the left one, the initial value is larger, and for the right one, the initial value is smaller. So for the top dimers, the relative orientation of two subunits are different, and the above one, the relative orientation of two chromophores is different. So in any case, the initial value can be different for different relative orientations. So we focused on the initial value. And the anisotropy up to 0.4 nanoseconds are like this. And we measured at higher concentrations and found that the initial value converges at higher concentrations. The initial value converges at higher concentrations, suggesting that there are only dimers. So the converged anisotropy value is 0.24 for EYFP and the different value of 0.34 for EGFP. Using these two values and the equation, we determine the R FRET, the anisotropy after FRET. And using that value, we determine theta t, the angle between two transition dipole moment of the dimer, donor and the acceptor. And we determine the theta t values to be 45 degrees for EYFP and 27 degrees for EGFP. So we found that the relative orientations are different between EYFP and EGFP. So the different theta t values can be understood like this, as follows. There are two possibilities. The first possibility is the relative orientation of two subunits are different. between EYFP and EGFP. And the second possibility is the relative orientations of two chromophores are different between EYFP and EGFP. It is currently unclear which is more accurate, but this is the first determination of relative orientations for fluorescent protein dimers in solution. So we wanted to know the origin of the difference. So we prepared these two mutants. In these mutants, one of the 5 different residues has been interchanged. For example, the 65th residue is glycine for EYFP and threonine for EGFP. So we prepared EYFP G65T and EGFP T65G mutant. If the anisotropy are different from those for the wild type, that residue is important for dimerization. And these are the results of the mutants plotted in black. And for comparison, the corresponding wild type is plotted in orange for EYFP and green for EGFP. And we found that the largest change was observed for EYFP G65T mutant. For EYFP, by this mutation, the initial value increases, indicating that there are no dimers. This behavior is very similar to the EGFP wild type, that green one. And for EGFP, by this mutation, the change is not so large, but the initial value decreases, indicating there are more dimers. So we concluded that the 65th residue primarily causes the difference in dimerization. The 65th residue is one of the 3 residues that forms the chromophore. And you can show that orange and green part of the 56th residue. And as I mentioned earlier, this difference induces different hydrogen bonds around the chromophore. The chromophore is, of course, inside the beta barrel. So the 65th residue is also inside the beta barrel. So the 65th inside the beta barrel changes the relative orientations of 2 subunits or 2 chromophores. And this is the conclusion of the second topic. EGFP and EYFP form dimers. However, their dimerization efficiencies and the relative orientations of 2 transition dipole moments are different. And we conclude that the origin of the difference is primarily in the 65th residue. So this is the final topic. In this study, we focused on calcium ion sensor protein, yellow chameleon 3.60, YC3.60. YC3.60 is widely used to monitor the concentration change of calcium ions in living cells like these movies. YC3.60 is a tandem protein with CFP, enhanced cyan fluorescent protein, and Venus, one of the YFP mutants. And in between, there is a calmodulin unit, which captures calcium ions. In the absence of calcium ions, left-hand side, the excitation of CFP gives the CFP fluorescence. But in the presence of calcium ions, FLET occurs from CFP to Venus, and the Venus fluorescence is observed. So FLET is important for this mechanism. But the FLET mechanism of YC3.60 is poorly understood. So we studied about this molecule and found that there are many structures of YC3.60 in solution, and the heterogeneity is induced by the dimerization of CFP and Venus, and it's very important for the FLET mechanism of YC3.60. So let me show you the results. This pink one is the absorption spectrum of YC3.60. The left one is for ECFP part, and the right one, strong one, is for the Venus part. When we excite the ECFP part at 400 nanometer, we obtain these fluorescence spectra. The cyan one is only ECFP, and the red one is YC3.60 in the presence of calcium ions. The ECFP fluorescence is weaker, and the Venus fluorescence is stronger. This is due to FRET. And the blue one is in the absence of calcium ions. The strong Venus fluorescence is observed. So FRET occurs even in the absence of calcium ions. So we measured time-resolved fluorescence spectra of YC3.60 in the presence of calcium ions, the left-hand side, and in the absence of calcium ions, the right-hand side. And the Venus fluorescence was observed just immediately after excitation. This is due to FRET. And because this FRET is faster than 20 picoseconds, we call this FRET fast. And also, the Venus fluorescence becomes stronger at later delays in both conditions. So this is also due to FRET. So we call this FRET slow. So we found that there are two different FRET processes. One is FRET fast and the other is FRET slow. So to study FRET slow, we measured under the magic angle condition. And for the ECFP fluorescence, the first decay component with a time constant of 27 picoseconds was observed. And for the Venus fluorescence, the corresponding rise component was observed. So this is the time constant of FRET slow in the presence of calcium ions. And we measured at 3 different concentrations, and there are no concentration dependence. So for FRET slow in the presence of calcium ions, FRET is only intramolecular reaction. So in the absence of calcium ions, the rise component becomes slower compared with that in the presence of calcium ions. And there is concentration dependence. So FRET slow in the absence of calcium ions is both intramolecular and intermolecular reactions. And we also performed anisotropy measurements, and the decrease in the initial value, in the presence of calcium ions, the decrease in the initial value is significant. So FRET fast is dominant. And in the absence of calcium ions, the decrease is not so large. So FRET slow is dominant. And the initial value is slightly concentration dependent. So FRET fast is mainly intramolecular, and intermolecular is rare. So using this initial value, we determine the angle between CFP and Venus in this timer. And we determine the theta t value to be 63 degrees. This angle is different from those for the EGFP dimer and for YFP dimer. It's very interesting that different FRET pairs have different relative orientations. And based on these observations, we can depict many structures, different structures of YC3.60 in solution. In the presence of calcium ions, there are at least 3 structures, and this pink one is the most important structure for FRET. Because this FRET is faster than 20 picosecond, dimerization is tight and the structure is rigid, and the angle is 53 degrees. And in the absence of calcium ions, there are at least four structures, and these two structures in pink are most important for FRET.
5 minutes more.
Okay. I will finish. So that left one is intramolecular, and the right one is intermolecular FRET. So the structural heterogeneity is induced by the dimerization of CFP and Venus, and it's important for the FRET mechanism of YC 3.60. And this is the conclusion of the third topic. In YC 3.60, the dimerization of CFP and Venus is induces structural heterogeneity, and multiple FRET processes occur both in the presence of and in the absence of calcium ions. So in these studies, we have demonstrated that the different fluorescent proteins have different dimerization behaviors. So we want to study about other fluorescent proteins, and we want to find a generalized view of dimerization behavior of fluorescent proteins. We believe that that information is useful for the better imaging using fluorescent proteins. Thank you for your kind attention.
One question we can take from the audience, if there is any. Yes. Yes. Can you give the microphone? Give one microphone.
Ma'am, how can fluorescent protein help in the studies of cancer microbiology?
Start it.
How fluorescent proteins can help in the study of cancer microbiology?
I see. So there are many kind of things, but one is a protein characteristic for cancer cell can be monitored using fluorescent proteins. So if this is a cancer cell, we can detect the fluorescence of fluorescent proteins. Yeah, it's already used for not only cancer, but any Alzheimer or Parkinson diseases. Yeah.
Yes. Any other question? Okay.
Ma'am, there is a little question I have. Aquaria victoria is generally a jellyfish, so it commonly available and highly active towards fluorescent. Except Aquaria victoria, can we use any other jellyfish which will be our fluorescent study, which can be, and it will be cheaper from other sites?
Mainly jellyfish and coral. Many different types of coral have red fluorescence. Do you know that coral in the sea?
Yeah.
That color is from fluorescent protein.
It means same type of GAP protein and YGP protein, same interaction will be there as like coral. It will take.
That's very. Yeah, thank you for the question.
Okay.
It's different.
Okay.
Yeah.
Another question is very simple question, ma'am. We are detecting the calcium ion by this fluorescent study. So can we detect any other hazard metals like heavy metals like cadmium or any arsenic that will be easier for our?
Yeah. So it depends on the interaction parts. In that protein, we use calmodulin which captures calcium ion. But if you use other part, such as crown 80 or something, you can select any metals you desired.
So we can, as usual, our requirement, we can study the fluorescence study. As our requirement for the any other hard metal, carcinogenic metals like cadmium and arsenic, we can use the GAP protein for our the study. Okay, ma'am. Thank you. Thank you, ma'am. Thank you so much.
Thank you.
Thank you, ma'am, for showing an insightful research on fluorescent proteins which shed light on their complex dynamics and Fret mechanisms. Now we request Professor Satyaban Jaina to felicitate Dr. Hosoi. Please, sir. We also welcome Dr. Abhinikumar Sahu and Dr. Deepa Nag on the stage to felicitate Dr. Hosoi. Please give a big round of applause for Dr. Haruko Hosoi.
Next, it is an honor to welcome Professor Dr. Shumanta Kumar Padhi, Associate Professor in the Department of Chemistry and Chemical Biology at the Indian Institute of Technology, ISM Dhanbad. Dr. Padhi is an accomplished and visionary inorganic chemist whose cutting-edge research explores the frontiers of homogeneous catalysis, artificial photosynthesis, and functional molecular systems for energy conversion. His work embodies both scientific depth and societal relevance, particularly in the field of sustainable energy. A recipient of the Best Graduate Award from Utkal University, Dr. Padhi earned his PhD in chemistry from IIT Guwahati under the mentorship of Professor V. Manivanan. His academic journey is marked by prestigious international fellowships, including the MEXT Fellowship in Japan, the World Class University Fellowship in South Korea, and visiting professorships at Eva Women's University and Lehant University, Sweden. In the recognition of his scholarly brilliance and dedication, Dr. Padhi has been honored with several awards such as the National Merit Scholarship and international recognition through SERB DST travel support. His active involvement with leading professional bodies, including the Japan Society of Coordination Chemistry, the American Chemical Society, and the Chemical Research Society of India, reflects his global scientific engagement and collaborative spirit. With his innovative approach, academic excellence, and inspiring vision, Dr. Padhi continues to make remarkable contributions to the advancement of inorganic chemistry and energy research worldwide. Today, Professor Padhi will introduce us to proton-coupled electron transfer, a key principle in energy processes such as photosynthesis, respiration, and CO2 reduction. We now invite Professor Dr. Sumanta Kumar Padhi for his talk on PCT, proton coupled electron transfer, bridging the walls of proton and electron dynamics. With a warm round of applause.
Many thanks to the organizers and Professor Avani Sahu for inviting me for this mega event. So my talk is completely based upon the evolution of a proton coupled electron transfer process and its role in carbon dioxide reduction. Okay, so I'll go to the introduction part simply. My talk will cover the introduction, then proton coupled electron transfer process and CO2 reduction, followed by the acknowledgement. So if you all consider the carbon dioxide reduction, so basically the world scientific system now in a progress towards the development of your chemicals as well as the energy for the requirement of a future. So if you consider here, actually this laser is not working by the way. So all the processes we need, whether we can achieve it in a sustainable trajectory or not, that's a questionnaire for us. So if you consider carbon dioxide now, so this process we can utilize the sustainable energy, whatever you have, let us say your hydropower or the wind power or the electrical power. So we can use this carbon dioxide reduction by using this sustainable energy to produce a variety of chemicals, or you can say the energy value added products to convert into that one. So let us say carbon dioxide. So carbon dioxide is the end product of your variety of materials. Let us say that is the combustion process end product of many materials of that one. So in these cases you are using this carbon dioxide in a circular economic process for you that you can convert that one by the electrochemical reduction of your carbon dioxide, and you can convert that one into chemicals or your value added products in a circular economic process. Now let us consider the carbon dioxide. So these cases I consider carbon dioxide as the dry ice and your hydrogen gas, that is the reduction, that is the fire. So this is basically the interaction of your dry ice and the fire, and what will be the product, that is the focus of our interaction. So look at there the carbon dioxide. So whenever we consider carbon dioxide, as I mentioned to you, that is the end product of your combustion at many cases. So it has a lower energy, that is the lower energy product in many cases. So if you consider that one and react carbon dioxide with a variety of partners, so that will give you the product. So these partners are usually basically the high energy partners. So let us consider water. Carbon dioxide likes to react with water to give you carbonic acid. It likes to react with the ammonia to give you carbamic acid, but it doesn't like to react with the hydrogen gas, which is a high energy partner, to give you other products, because CH bond formation is a very difficult process and eventually the CC bond formation also. So if you consider the reaction of a carbon dioxide with the high energy partner hydrogen gas, it's a high energy barrier process to give you varieties of products in these cases. So what you need actually, so to decrease the catalyst energy barrier in this process, you need a catalyst to design such that the carbon dioxide can interact with the hydrogen gas, which is the partner here, to give you varieties of value added product here. So that means the barrier decreasing is required by a catalyst that will decrease your activation energy barrier basically. So now if you consider that one, what is that catalyst we use? That is a redox catalyst. So if you consider catalyst, the potential you require basically it is added to the catalyst you have considered, and that reduces to, I think there is some problem in the fixing up of these slides. So the catalyst C goes to the reduced species C prime at a redox coupled C to C prime there, and which in turn provides the required number of electrons to the substrate to convert into the product. The substrate is here your carbon dioxide. So that will accept the electron and reduce into the varieties of products, whatever you need. It may be the direct electron transfer process, or it may be the proton coupled electron transfer processes, and the difference of your substrate redox potential to the applied potential, that's your over potential here. So now let us consider the carbon dioxide, which is the end product here, as I mentioned to you. So if you add 1 mole of hydrogen gas here, so 1 mole of hydrogen gas, basically that is 2 proton and 2 electron. So that will give you formic acid, which is the equivalent case of your carbon monoxide in this cases also, if you consider the electrochemical reduction process. So the next 1 equivalent of hydrogen addition, that will give you the formaldehyde, followed by methanol, followed by methane. So if you consider carbon dioxide to methane, it is a 8 proton coupled 8 electron transfer process, which is following 1 to 3 intermediate steps. It's a tedious and very difficult process to give you carbon dioxide to methane, which is a value added product, or you can say the energy in turn. So now we'll see, and I will come to your topic a little bit later. I'll go to little bit history now. So if you consider the history of coordination chemistry, basically the audience is mostly BSc and MSc students. So now I should consider a little bit history of this one. So if you consider the history of coordination chemistry, Arrhenius in 1903, he discovered the reaction of your cobalt-3 species with chromium 2, which oxidizes chromium 2 into chromium 3 and self-reduces into cobalt 2. So that time the Arrhenius considered that one, the naked ions, they are reacting with each other, okay, so that the cobalt 3, it oxidizes chromium 2 into chromium 3. Now go to Werner. So in 1913, he invented the process of your involvement of your primary and secondary coordination sphere. He told that it's not naked cobalt 3 or chromium 2, they are interacting with each other. Rather, the primary coordination spheres of those ions are involved in the reaction space intermediate formation. Now go to Henry Taibu. So in 1954, Henry Taibu, he invented the process of your outer sphere and inner sphere electron transfer processes, which is in turn gives you the more advances in your electron transfer process. Now it's not the end of the story. So if you consider Marcus, 1956, he gave the theory of your electron transfer processes and considering the reorganization energy and many other terms. Now I'll come to T.J. Mayer, 1982. He is the fellow who invented the proton coupled electron transfer process while conducting the water splitting reaction by using the ruthenium based catalyst, that is your so-called blue dimer. So it took Tom Mayer to consider this proton coupled electron transfer process. If I consider from Arrhenius 1903 to 1982, nearly 80 years it took to Tom Mayer to understand the topic of your proton coupled electron transfer process, and that's the role of a proton coupled electron transfer process in variety of redox processes. So as I mentioned to you, so Tom Mayer, he is the fellow who invented this proton coupled electron transfer while conducting the water splitting reaction by using this blue dimer ruthenium complexes. I am not interested to this one. Actually, this water splits into dioxygen and gives you 4 protons and 4 electrons. So now come to the topic, this proton coupled electron transfer, usually invented by or is called as the EH-PH diagram. He is the father of this EH-PH diagram, Marcel Pourbaix. So Marcel Pourbaix is the fellow who invented this topic, that is called Pourbaix diagram, and that gives you the changes in the potential with respect to your pH. So how the potential varies, it is just like your phase diagram. So this is called your electrochemical phase diagram. So electrochemical phase diagram, the means of that one is at various pH how the different species resides at a different potential. So now let us consider, I will give a little bit hint regarding that proton coupled electron transfer process. So let us consider a ruthenium torpidine analogous, but here that is the carbon analogous actually. So in case of torpidine, that is the nitrogen. So in the meridional fashion, your NCN coordination is there, and one of the apical position is coordinated with the chloride, and two of the positions, one in equatorial position, one pyridine, and other apical position is pyridine. So these cases, if you consider the ruthenium 2,3 redox couple, it appears as 0.1 volt in this case. Now go to the other redox couple, the next event, that one redox event. So that's a ruthenium 3 to ruthenium 4. So that occurs at a 1.1 volt. So if you consider ruthenium 3 and ruthenium 4 in these cases, the potential difference is almost 1 volt in this case. This is the 1 volt difference of ruthenium 3 to 4. So now, if I consider that one, you can see here ruthenium 2, 3 as well as ruthenium 3, 4, both are the flat lines. That means the potential is almost independent of a pH. Once you change the pH, there is no change in the potential of for the redox couple. Now look at the other one. So just to change this complex into the torpidine analogous. So if you change this complex into the torpidine analogous and replace this chloride by aqua moiety. So aqua moiety, that is your water coordination, it consists of your proton. So that means the protonation and deprotonation event can occur from this water coordination. So now in these cases you can notice here the ruthenium 2,3 couple, okay. So that event, it is a slanted line whenever you are increasing the pH, and eventually ruthenium 3,4 couple also a slanted line whenever you are going to the next event. But the gap between ruthenium 3 to 4 is just 1 volt. So you can see the role of a proton coupled electron transfer process here. How come it has changed the 1 volt difference of your in the previous complex NCN moiety cases, where there is no proton source is attached to the coordination of sphere of your ruthenium complex. But in the case of the blue complex, that is the ruthenium torpidine complex, where water is the proton source for the deprotonation cases, where the proton coupled electron transfer event is eventually it is taking place and reducing your potential from ruthenium 3 to ruthenium 4 by 1 volt of difference. So you imagine the energy of 1 volt of difference you can enjoy with the proton coupled electron transfer processes. So now I'll go to the topic, the proton coupled electron transfer process, how it is utilized in CO2 reduction, and why your CO2 reduction is a difficult process. So if you consider carbon dioxide, it has a very low solubility in the solvents, and the stability of your carbon dioxide, as I mentioned, it is the end product of combustion in the varieties of materials. So now the overpotential also, and hydrogen evolution reaction, that is a more competing reaction in the case of your carbon dioxide reduction. And the next one is the multi-step process involvement in the CO2 reduction, then the catalytic stability and selectivity issue. So look at there. So if I consider the carbon dioxide, okay, so it is called as a thermodynamical sink, because here the carbon oxidation state is nearly 4 plus, and it is a linear molecule with a non-polar nature, okay, and the energy of this one, the CO bond is nearly 750 kilojoule per mole. So now if you consider, let us add 1 electron to your carbon dioxide, which is linear in nature. So if you consider carbon dioxide, this is your sp hybridized carbon center is there. Now add 1 electron, the sp hybridized carbon dioxide carbon center, it will convert into your sp2 hybridized carbon center. So that will bend. That means if you add 1 electron, it will give a carbon dioxide radical anion. So that means the linear structure, it gets bent in these cases. So now in this case, you can say the sp hybridized carbon center, it changes into the sp2 hybridized carbon center. So what you see, let us consider it means a straight stick here. So straight stick, you want to bend that one. So that means you definitely you need energy to put the bent stick into a bent manner. So that's what it happens here. If I consider here, the scientist is bending the carbon dioxide here, the carbon dioxide molecule. So that means the 1 electron reduction of your carbon dioxide, it requires a heavy energy that is of a minus 1.90 volt, okay, at pH 7. So that is that much amount of potential is required, just a single electron reduction of your carbon dioxide into carbon dioxide radical anion, because it requires a large amount of reorganization energy. Okay. So now come to the proton coupled electron transfer processes, how it plays the role. So if you consider the two proton coupled two electron reduction processes, carbon dioxide, it can convert into carbon monoxide or it can convert into formic acid, but the four proton coupled four electron redox processes, that will give you formaldehyde, and 6 proton coupled PCET process, that will give you methanol, and followed by the 8 proton coupled 8 electron reduction process, that will give you methane. So as the number of proton coupled electron transfer processes, your redox event potential decreases, but the number of steps involved in the multi electronic reduction processes are high. So therefore this complexity increases and the difficulty of your conversion of carbon dioxide into methane also increases. Now look at there. So as I mentioned to you, whenever you reduce carbon dioxide by a 2 proton coupled 2 electron reduction process, so you have the two different options. It can either convert into carbon monoxide at minus 0.53 volt, or it can convert into formic acid by 0.61 volt. Okay, so that is versus your NHE or at pH 7. Okay, so now if you consider simply 2 proton coupled 2 electron reduction process, that is below 1. So in these cases, this redox event, it considers the potential minus 0.42 volt. So thermodynamically, so let us consider this is 0.42 volt. Now the next one is 0.53, the next one is 0.61. So the process thermodynamically feasible is proton reduction first, because minus 0.42 volt that occurs first, that event, followed by your carbon monoxide, followed by your formic acid. So thermodynamically this process should occur so that your hydrogen evolution reaction, if your CO2 reduction needs a proton source, then eventually hydrogen evolution reaction will be the much faster reaction than comparison to your CO2 reduction reactions to give you carbon monoxide or your formic acid. But the other events, if I consider minus 0.38 and minus 0.24, so by that way it is much lower potential as compared to your proton reduction. So that means those cases hydrogen evolution reaction can never be a competing reaction to your CO2 reduction. Okay, so now in these cases, if I consider the thermodynamical point of view, so you have just like a competition. So your hydrogen evolution reaction, that will be the gold medalist. Now the next one will be the silver medalist, that will be your carbon monoxide. Then the bronze medalist will be your formic acid formation. So now let us consider, so if you compare this CO2 reduction with the hydrogen evolution reaction, I think there is some problem in the slide formation. So this case is hydrogen evolution reaction that requires the hydride formation as the intermediate, whereas your CO2 reduction process that requires your CO2 minus or your formate, or you can say the CO2 minus adduct as the intermediate in these courses. So that depends upon the pK of your acid addition. If you add a strong acid, definitely upon the reduced or rich metal center, it will accept the proton to give you metal hydride formation rather forming into metal formate intermediate. So in those cases, your hydrogen evolution reaction will be much faster as compared to your CO2 reduction reaction. So hence, in these cases, while you are designing your catalyst, your ligands play a bifunctional role. You must play a bifunctional role here, okay? And you must tune your proton addition so that the peak, you should use a weak acid source such that it will overcome your CO2 reduction reaction than that of your proton reduction reaction in these cases. So that will give you a better output for your CO2 reduction reaction. So now I'll give some outputs of our laboratory, which has been recognized as a cover feature for the competing reaction of your carbon dioxide and your hydrogen evolution reaction. And this is done by my previous student, Dr. S.K. Saming Akhtar. So these cases we have synthesized three complexes out of this parent complex, your copper DPA complex. DPA is your dipyridine carboxylic acid. So now in these cases, this parent complex we have synthesized and used with another pendant other ligands. So those are your bipyridine analogus. So that is your pyridyl naphthyridine or pyridyl quinoline. So pyridyl naphthyridine I have means your short form here pyridyl pinap and naphthyridine as PQL. So these complexes we have used as the CO2 reduction catalyst in these cases. All of them are of a square pyramidal in nature in this case. Now the peculiar behavior in this case is, if you consider this catalyst here, so the pK of all these cases, although in the case of your pyridyl naphthyridine there is a nitrogen atom at this R case, so that doesn't accept the proton, because in theoretical and experimental cases also we have seen that is the low electron density at that nitrogen position, and under this aqueous conditions your carboxylate that cleaves and it undergoes protonation and deprotonation process to give you the pK of your at 4.5 for the first complex, that is the nitrogen substitution R, and with the CH that is 4.4, which is a means a natural nature of your carboxylic acid pK, that is 4.5 and 4.4. So this was also we have found by the means visible absorption spectroscopic methods. So the changes in the absorption spectra at 335 and 296 it is visible here, and the pK fit it gives you 4.4 in the case of complex 2 here and 4.5 in the complex 1 there. So now in these cases we have means pointed out the cyclic voltammogram of these complexes, which gives you a irreversible nature for the redox event of a copper 0 and a copper 1 in all the three cases, and followed by your ligand based redox events in all these cases, the other features. So now if I consider here the under nitrogen atmosphere, the first spectra is your under nitrogen atmosphere, and if you consider the carbon dioxide atmosphere, there is a single directional increase in the catalytic current, which clearly indicates that your catalysis of your CO2 reduction event occurs whenever you purge your carbon dioxide into the complex solution. So now again what we did, we have added some amount of proton source, that is your water. We have added 1.1 molar of water into that reaction medium. So each cases you can see the blue trace of that redox phenomena. So again the catalytic current increases in the single directional event, that one we can say. So those cases that clearly indicates that the proton has the role in increasing the catalytic event, and it is a general phenomena of your proton coupled electron transfer process. So now look at there. So every cases we have increased the catalyst concentration also, and we have noticed that the carbon dioxide reduction, it is directly proportional to the catalyst concentration here, because the redox event of your catalytic phenomena for the CO2 reduction that directly increases as you increase the catalyst concentration in each cases. The next case is the addition of a proton source, that is your water as well as your D2O. So we have used water as the proton source in one case. So every cases that indicates that if you add water, the catalytic current increases, and also if you add deuterated water, that catalytic current also increases. Then we found the rate constants for both the water medium and for the D2O medium, and whose ratio, this is called your kinetic isotope effect. So that gives you higher than 1.5, 1.4, 2.2, which is more than your 1.0. So that effect, if I consider there, so in these cases, if I consider the rate of the reaction, that is your Kh by Kd or kinetic isotopic effect, which is higher than 1.5, and it clearly indicates that your proton coupled electron transfer process plays a key role in the rate determining process of your CO2 reduction, okay, while you are reducing carbon dioxide into the other products. So now in these cases, we have seen what are the products that those has been generated from the gas chromatography means outputs. So here carbon monoxide as well as hydrogen gas were the gaseous products in means as the products that those are found from the 2 proton coupled 2 electron reduction of your carbon dioxide into carbon monoxide or your hydrogen gas in these cases. So the left hand side is your carbon monoxide in this case and the right hand side is your hydrogen gas. So as I mentioned to you, whenever you are using 2 proton coupled 2 electron reduction process, thermodynamical 2 proton and 2 electron, they can self react to give you hydrogen gas also. So here that reaction also happens. So that means it indicates that your carbon dioxide to carbon monoxide formation and your proton reduction both are a competing reaction here. So now if you see in these cases, then what we did, we have used the residual gas analyzer, that is the mass spectrometry. How come this means results it is giving you, which is the faster process in these cases. So now in these cases you can see here, the first case you can see up to 4000 or 5000 seconds, the hydrogen evolution takes place fast, followed by your 12CO, that is the 12CO2 means carbon dioxide we have considered. Now the isotopic labeled 13CO2 we have taken. So that cases you can see up to 800 seconds fast hydrogen evolution occurs, followed by your 13CO. So that clearly indicates that hydrogen evolution reaction occurs fast in comparison to your CO2 reduction to carbon monoxide evolution. So these events also followed in the means other catalyst also the similar way. So this also clearly indicates that your proton reduction can be a better competitor to your carbon dioxide reduction. So you cannot get rid if it is thermodynamically involved. So in all these cases you can see nearly above 85% or 80% of your Faradic efficiency was for your carbon monoxide, while above 15% or nearly 15% of Faradic efficiency for hydrogen gas. So these events are clearly indicating that your proton reduction is a competing reaction to your carbon dioxide reduction. So now in the cases of your in situ spectroelectrochemical IR, so here we have observed what is the intermediate it is there. So you can see the natural cases, that is 2326, that is your carbon dioxide stretching frequency, asymmetric stretching frequency. Now if you consider the adduct, that is the reduced product adduct 1628, which eventually considers from a range of 1500 to 1600 depending upon the coordination sphere. So this first complex, the increment of the means your peak at around 1620, that clearly indicates the formation of your metal CO2 anion peak, or you can say the format coordination. And in the other case also the 1515, that clearly indicates the format formation in the complex 2. So now we have used the spectroelectrochemical UV visible spectroscopy as the intermediate studies. So these cases what we did, we have studied this one at minus 1.8 volt for the bulk electrolysis process. So these cases at the reducing this complex at minus 1.8 volt under carbon dioxide atmosphere. So we have noticed that in each case the copper 2 reduces into copper 1, followed by the metal to ligand charge transfer in all these cases. Okay. So now consider the complexes here. So if you consider the parent complex to the other two complexes, so the resting potential in all the cases, because we have considered the copper 2 complex, it was earlier the copper 2 complex, followed by the reduction. As I mentioned, we have noticed the UV visible spectroscopically, the copper 2 reduces to copper 1 first, and that also we have noticed in the case of your redox event, that is the cyclic voltammogram of your complex, that gives you the information that the resting potential changes from copper 2 to copper 1 here, and we left the solution after CO2 reduction for 3 days. So it eventually gains the or aerial oxidation occurs, and the copper 1 regains the copper 2 species after 3 days. So all the cases we have also found the you can see the morphological study we have done for the electrode surface also. In all these cases, the atomic weight percent deposition of your copper was very negligible, that is 0.05% in the complex 1 case and 0.01% in the complex 2 case. So which clearly indicates that the total catalytic process is your homogeneous in this case. Now we'll have conducted the DFT studies for interpreting the mechanism of this CO2 reduction. So in each of these complexes, so your starting complex is your copper 2, so it undergoes 1 electron reduction to give you the copper 1, followed by another 1 electron reduction to give you the either the bipyridine analogous, that is the bipyridine analogous reduction, that one. Of course, the cyclic voltammogram is a versatile tool to give you all the informations, that one. So then it can go the another electron reduction to give you the reduced species at the carboxylate anion, and followed by the protonation to give you the copper 1 hydride. The same phenomena we have tried also after copper 1, we have reduced that one into the reduced species, that is the ligand based reduction. We added proton, so which is a very uphill process. So of a minus 4.82 kilocalorie, that one. So in that cases you can see the other one, whenever you add another electron, that is a downhill process that requires minus 51.3 kilocalorie per mole. So that means we didn't consider the EC phenomena in these cases, rather we considered the electrochemical followed by chemical and followed by another chemical process for the CO2 reduction. So that means in these cases, after forming the copper 1 hydride, it can react with the copper 1 hydride, the proton source, to release the hydrogen gas and to get you into the previous, you can say the precursor complex copper 1 species is returned back, or followed by the addition of your CO2, which gives you the formate complex, which we have already noticed in the adduct formation in FTIR spectroscopy also. So that interaction, it gives you the water release and followed by the carbon monoxide release, and with the return back into the precursor complex, that is the copper 1 complex. So both the cases, it follows the similar kind of your catalytic path in these cases. So I will summarize my electrocatalytic processes here. So we have designed several copper based molecular catalysts which can be used for the carbon dioxide reduction, and in all these cases your proton coupled electron transfer process plays a critical role for the reduction of carbon dioxide into carbon monoxide, where proton reduction itself becomes a competitor to your CO2 reduction into carbon dioxide to carbon monoxide, since both are two proton coupled two electron reduction processes. And as I mentioned to you, and for the first time we have detected that one, which whether hydrogen evolution reaction or your CO2 reduction, the time based evolution of gases that has been used by your residual gas analyzer, which has given you the output of the kinetic phenomena, that whether hydrogen evolution reaction occurs fast or your CO2 reduction occurs fast. So that I have already give you the interpretation by using the residual gas analyzer. So thank you. These are my collaborators and some of my students and my group members here. And I also thank to the funding resources from ACRB, our stint Sweden, and our IISM Dhanbad and CSR for funding this kind of resources. This is my present group here at IIT ISM Dhanbad, and this is our beautiful building as a replica of your Royal School of Mines built by Britishers. Many thanks to all of you for your kind attention.
Okay, Sumanta, before the audience there is any question, I will ask you.
Sure.
He was once upon a time our student, and he topped in his batch, I remember. Then worked with Manivarnam.
Yeah, Manivarnam.
So I regularly visit IIT Hyderabad,
Guwahati.
Guwahati, and then I have a question. In one of the slides,
sir,
you showed that the formation of singlet oxygen. Now
No.
why? No, water molecule, two water giving you O double bond O.
That is dioxygen.
So the fundamental question is, essentially molecular oxygen is a triplet oxygen. Means O single bond O dot and dot. It's a diradical. But in organic chemistry, we look for singlet oxygen. Singlet oxygen O double bond O, because that we use in preparing Diels-Alder reaction,
Yes.
heterodiels-Alder
That's
reaction,
true.
endoperoxides.
Yes.
So, and normally the procedure is you take singlet oxygen, then H nu in presence of a photosensitizer.
Exactly.
That converts to this one. But it's a difficult process. And in organic laboratory, we don't require O single bond O. We require O double bond O.
Exactly.
Right. So, my question to that slide is, how can you convert, other than the Rose Bengal photosensitizers, forget about that. These are old chemistry.
Sir.
So, using your procedure, can you convert triplet oxygen to singlet oxygen easily using a catalyst?
Sir, it is a difficult phenomena because
Yes.
if I consider, if you do have a coordination means environment which can trigger to your means a singlet to your triplet, so that is possible, because in our cases what I mentioned to you.
I have seen that slide.
Yeah.
But my question is, you think of it because it is a challenge.
It's not that easy, but it's not
It
a
is-
regular
it's a
phenomenon.
difficult thing, because converting triplet oxygen to singlet oxygen, that can only be done in presence of a photosensitizer.
Yes.
But without a photosensitizer, using a catalyst, say copper based or rhodium based,
Not
ruthenium
that
based,
easy. Not that easy. Controlling
so-
that one, it will not be
so
that easy.
This is a challenge to the inorganic catalyst people to think of this.
Because they will eventually try to couple with each other.
Yes, because there will be self-coupling.
Coupling.
Instead of forming this triplet to singlet,
Singlet.
it will undergo self-coupling.
Coupling.
So think of, I mean, this is a question for you to think and then give
Sure.
the task to your students.
Sure.
Okay. So any question from the audience? One question we can take.
Sir, you have told that in carbon dioxide, carbon undergoes sp hybridization. After accepting one electron, how and why it undergoes sp2 hybridization?
So that's what, because if you means consider one, where is the means carbon center, that is the 4 plus oxidation state in that cases, okay. So if you consider one electron, okay, so where does that electron goes in that case? Go to the molecular orbital theory of your carbon dioxide, and that electron goes to where? So those cases, in these cases, if you consider the added electron, it goes to which orbital of your carbon center. That decides that in case of your carbon dioxide, if you add one electron, your bond breaking takes place and it undergoes breaking up of carbon and double bond O bond formation to give you CO radical anion. So it breaks the bond and undergoes the cleavage of your sp hybridized carbon center into the sp2 hybridized carbon center by a bent form. Because
it enters into the SOMO.
SOMO.
It doesn't enter into the HOMO, highest occupied molecular orbital.
Yeah.
It goes to SOMO because singly occupied
Molecular orbital.
It goes there.
And
okay, you can have a discussion with him. He will be there. So, in the absence of any other question, let us give a no. We will discuss at the lunch because shortage of time. So, let us thank the speaker, Professor Sumanta Padi from IIT ISM Dhanbad. Okay.
okay, thank you.
Thank you, Professor Padi, for for that insightful exploration of proton-coupled electron transfer. Let us all express our appreciation with a big round of applause, and I will request our jury, Professor Satyaban Jaina sir, our principal, Dr. Deepa Nag ma'am, and Dr. Abani Kumar Sahu sir, to honor Professor Padhi.
Let us now welcome Dr. Sudhanshu Shekhar Tripathi as he presents his talk on decoding complex molecules, basics and applications of 2D NMR. Sir, please.
But I will take 40 minutes, Chairman sir. Lunch is yet to arrive. I have delayed it. It will come late. Hello everyone, the young students of this great college, the galaxies of scientists, illuminaries coming throughout the world, from African countries to the country of rising sun, Japan. I am really humbled, honored to have been invited by Professor Dr. Abani Sahu to give a lecture. And I really congratulate the principal ma'am, Professor Dr. Deepa Nag, to have organized such a wonderful international level seminar. At least now we'll be doing, I apologize to my scientific fraternity who have come with a lot of data, to present a lot of data. I will beg your apology. I will be mostly student centric in my approach. I will be presenting whatever little on spectroscopy on a popular level. And because I don't do any research for the last 2 decades or more, since I had taken voluntary retirement from Ravensa, the then Ravensa College, now the great university, I have been engaged in popularizing, oh, why I'm standing here? Why I'm standing here? Yes, I have been engaged in popularizing chemistry, our religion, chemistry in school level. Basically, I'm a school teacher and have been elevated by the grace of this college to address this august gathering to speak a few words on spectroscopy. And the students, as Professor Misra was desperate to interact with the students because he was transacting in the level of a teacher rather than a scientist, although he is a grade 1 scientist. So I will be doing in the teacher level only. I am not a scientist at all. Now, while I'm talking of this electromagnetic spectroscopy, I beg to differ from what Professor Misra said, that this UV visible and IR, I take it as optical, while I will be in my stories, the small little stories that I will be telling to you will be using the electric vector as well as the magnetic vector of the electromagnetic waves, as he said, they are orthogonal to each other. So, ranging from gamma rays, Mossberg spectroscopy, picometer range, X-rays, XPS, UV visible, our most favorite electronic spectroscopy, UV visible, fluorescence, IR, vibrational spectroscopy, IR, Raman, microwave, rotational, radio waves, NMR. Now I have a question for the students. How many of you are below +3 third year? Is there anyone who is +3 first year or second year? Please raise your hand. Then put cotton on your ears. Tula de diyo. If at all you can answer, it will be my pleasure. If not, it's okay. Now the rapid fire round starts now. Mossberg spectroscopy to NMR. I will ask you whether it is absorption spectroscopy or emission spectroscopy. A or E? You will answer A or E. A for absorption, E for emission. Mossberg, your time starts now. Mossberg. It is absorption. And X-rays, emission of the core electrons, UV visible, and that to UV visible. No absorption, fluorescence, emission. What about IR? Absorption. Raman? I'm sorry, it's not exactly emission, it is inelastic scattering spectra. Is neither true emission nor true absorption, is inelastic, as Professor Misra was saying. Inelastic what? Inelastic scattering spectra. What about microwave rotational? Absorption. What about NMR? What about NMR, about which I will be talking a little bit? Of course, I will be talking about pure organic chemistry. Pure organic chemistry, which the undergraduate students, and you guys will like it, involving aldol condensation, Michael addition, that also will be there in the part of my program. But what about NMR? At this present day, when pulsed Fourier transform is the norm, nobody uses in our time. Remember, Professor Jena, we were doing at that time a continuous wave NMR came to Professor Dr. Rao's laboratory, and to scan from the upfield position, setting TMS at 0 down to 15 ppm, it was requiring 20-30 minutes. Gone are those days. Now pulse, microsecond, millisecond pulse is doing the magic, and you are repeating the pulse and accumulating the spectra. So what about NMR spectroscopy now? Absorption or emission? E or A? It is emission, yes, when the magnetization vector is tipping. After that, when it is relaxing, we are acquiring the data. So this is during emission time we are taking the spectra. So nowadays NMR is an emission spectrum, not absorption. Gone are those days. Now I will be talking about, as I told, that I will be harping on a electric vector thing and NMR thing. I was really excited to get a paper from Seoul National University. I was really excited. Simple organic chemistry. They took, because they were using it in a biological sample in the cancer research, they were taking 2-oxoglutarate. Don't be confused, it is glutaric acid, but in the cell it remains as methyl ester. So this is 2-oxoglutaric acid. I am saying 2-OG. 2-OG, and they added, simply they have added a diamine. This is a primary amine, this is a tertiary amine. N-N-dimethyl ethylene diamine. N-N-diethyl ethylene diamine called DIDA. Remember, I will be talking DIDA, and this is 2-OG. So they found the reaction between 3 molecules of 2-OG with 2 molecules of DIDA gave a very interesting compound, very interesting. That is called DPPP. DTPP, I will tell you what is that. It is giving a bright blue fluorescence, just like copper tetramine copper 2+ complex. So now this is nothing, no catalyst, nothing. Methanol is the solvent, room temperature overnight. DIDA and 3 molecules of 2-OG, 2 molecules of DIDA, and believe me, the way they have characterized the molecule, it contains 2 cyclic rings, one is a pyridone ring, the other one is a gamma lactam ring. The way they not only have prepared successfully, but also have characterized the entire molecule with NMR, mass, everything. With such an accuracy, I was amazed. Now, there is another question for the students. Please allow me. Now, tell me, what is the difference between this bright blue color that you are seeing from DTPP, which is having a fluorophore, is a fluorescent material, and tetramine copper 2 complex CuNH3 whole 2 plus, that is also looking like the same color. And this is a very simple question, but allow me, Professor Misra, see, he is laughing with his heart's content, but I am asking this question deliberately to the students to make me feel that I am not a school teacher yet. I am popularizing chemistry in school level, that is my work, through my society called the uranium, not uranium, the uranium. So, any question, any answer? I will not embarrass you. Instead, I will tell you the answer. Why this is blue, copper tetramine is also blue. Why? What is the difference between this? The optics behind it or the physics behind it? Any student? No. Okay, let me tell you. This is not looking blue as such. You are irradiating with a monochromatic ultraviolet light. Then only it is going to the higher excited level, from the ground electronic state to the higher excited state to the higher vibrational level of the excited state, and then with internal conversion it is coming back to the ground vibrational level, and then when it is falling down to the ground electronic state to different vibrational levels, it is giving a broad peak, and the lambda max is 3413. So, this is an emission spectrum where the incident radiation is ultraviolet, invisible. This is invisible unless you throw a xenon lamp. Unless you throw a xenon lamp in the dark room, you can't see the phosphorescence. On the other hand, copper tetramine is an absorption spectrum, because sunlight, it is absorbing which color? If it is looking blue, it is absorbing its complementary color. What is that? Orange. So, it is absorbing orange color and transmitting the blue color. So, that is the absorption spectrum of tetramine copper, which is a DD transition, as the inorganic chemistry will tell, DD transition that absorbs the orange color, and the transmitted color is the complementary color of the blue, and we are looking. So, that is absorption and this is emission. And now coming to, this is the same, this is the absorption peak of DTPP, and this is the emission fluorescence peak. Now little bit of organic chemistry, which will definitely excite not only to the students, but also the professor of organic chemistry, my elder brother, Professor Jaina. He can find fault to anything that he sees in organic. Organic is in his gene. Okay, then now I don't think you will find any defect, because this is a Korean paper, and I was really amazed to find this is the first molecule of 2OG. No, there is nothing. First molecule of 2OG, and there is simply a nucleophilic addition, and followed by dehydration to form an imine. So, this is the DIDA part, this is the 2OG part, this is imine. Then aldol condensation will happen with the second 2OG. The second 2OG, one water is already lost. You count how many water molecules will be lost, one water is gone, and then there will be aldol condensation. It is not exactly aldol, this is the aldol counterpart, this is the carbanion will be formed here, the acidic position, and this will attack here, and this will be an aldol. See the aldol here, aldol. There is no aldehyde, this is the counterpart of aldehyde, and then on heating, just left side another water molecule, not heating, oh I am so sorry, it happens as such. Water molecule goes and it gives this. See this one, now see this one, a double bond has been formed. So 2 molecules of water gone, then automatically this carbon dioxide is lost, this part is gone, and then the third 2OG has come. The third 2OG, please bear with me, please give me a good silence. Even if you cannot make out what is going on, please give me a good silence at least, so that others who are giving their attentive attention will not be deprived of listening to me. And I'll be going away as long as I am creating some excitation in you, just like the excitation spectra in fluorescence. I will be there, otherwise I will be going away. Rather, I will ask the permission of Professor Jena to allow me to sing a song for you, because I am an amateur, I am an amateur singer, so that I can do that for you. Oh. Okay. Okay, he is allowing me to sing a song at the end. Okay. Oh, then I am gone. Then I am gone. I am gone. See, now the carbon dioxide molecule is gone, then go for second aldol. Second aldol, double bond is here, and this carboxyl group is here. This is the acidic position which attacks this, the nucleophilic attack, and then in the same step I have shown water elimination, and come to this, there is this double bond. New double bond has been formed here. This new double bond has been formed here, and this DIDA part I have thrown it to the left. I have thrown it to the left. I will show the cyclization. Before that, the second DIDA is coming to go for a Michael addition. 1,4 addition, this lone pair is attacking to the 4th position, this coming here, this is coming there, so that you find here the NH is here, the other DIDA is joining here, the first DIDA has been sorted to the left and now is ready for cyclization. This is NH is here, NH is here. This is going for a cyclization, one water molecule lost, and that is another water molecule lost is here. So a 5-membered ring C here, there will be 2 water molecules lost, one carbon dioxide automatically goes here, this carbon dioxide goes here, this, and ultimately you are getting which carbon dioxide goes, this one. See, this one is missing out. No, this one goes for cyclization, I am sorry. This one, yeah, this one goes, and you see this one, finally you are getting this compound. This is a pyridone ring and this is a gamma lactam ring. DIDA is appearing as a dangling, I am telling dangling, and this is dangling here. This has a great role to play. This is dangling, and these are the two. The fluorophore is this part, and this is DPP, DTPP fluorophore, and the name is huge. Let us not go into the names. Name is very big. Now, this is a part of the story, and I will tell you how this is DTPP has been characterized by 2D NMR. Unless and until the intervention of 2D NMR, you cannot unambiguously, without any iota of doubt, you cannot characterize, you cannot establish the structure. Coming to my story of 1D NMR. 1D NMR at a higher field strength, it is not bad, it is really good. A lot of information, once usually I collaborate with James. He is a professor, organic professor like him, but he is a spectroscopy person. He is UCI, University of California, Irvine, and I used to stay 1 hour behind Irvine in San Diego with my sons. I collaborate with him. I used to find, while authoring a book, I find the glycerol. This is glycerol, our ordinary glycerol. See, the chemical environments are so close that we in 100 megahertz, I found a very jumbled up, the proton peaks are very jumbled up, because the ppm range is very small, 15, while in carbon NMR it is 250. So sensitivity, the resolution is not a problem in carbon 13 NMR once you decouple it. And we really decouple, broadband decoupling we do for carbon 13 NMR, but proton NMR, is a very big problem, particularly in biomolecules when protons in multicyclic rings are having nearly identical environment. To assign their positions and to establish this structure is a hell of a job. But for simple molecules, now I asked him, why not you go for a higher 600 megahertz or say I don't know 600 or 400 megahertz machine and do it for myself, do it for me, and whether it is a simple what is called the first order spectrum you are getting, or you are getting a non first order spectrum, therefore you go to 2D. So then he did it, he found that because of the steric, because of strain in the free rotation, these two protons are diastereotopic. This is a chiral center, and as you know, methylene protons adjacent to chiral centers are non-equivalent, they are not shift equivalent, they will have a J2. So what we got, that HB they are identical because of the sigma plane symmetry, SC are identical, HA is separate. So we get 3 peaks, and the multiplicity of this SC peak is a DD, doublet of doublets, with a coupling constant, the data is not here, is 10.2 and 6.5. So also in case of HB it was say 10.2 and 4.4, and then while we studied the multiplicity of HA, we found it is a TT. What is a TT? Table tennis. It is a triplet of triplets, and initially we thought it is a non first order spectra. It is looking very jumbled up, but when we really thought let us do it again and again, we found it is a overlapping TTs. Now see, 1:2:1, then the second triplet is 2:4:2 here, they have been trespassed to the other area, and the third triplet is here 1:2:1. So is a TT, and we surprisingly found that 6.54 because of the dihedral angles are different. Karplus plot, you remember this HAC, AC coupling constant is 6.5 while AB coupling constant is 4.4. So whatever information we got 6.5, 4.4, same information we found in the TT with 2 coupling constants 6.5 and 4.4. So this is my looking at 1D NMR, daag achhe hain. We have a slogan, daag achhe hain, 1D NMR is not bad. If you go for a higher resolution, high strength, magnetic strength 1D NMR, it can provide very, very good information, particularly in small molecules. But when you go to large molecules, we have to say hi and salute to 2D NMR. In 2D NMR, actually it is a 3D plot actually. As you know, there are 2 frequency axes, F1 and F2, and the intensity axis is a mountain. We caught it and we take the contour map and we study them. So this is a 3D plot. How do we say 2D NMR? Because 2 frequencies are involved. And remember, how many of you are from PG? Raise your hands please, postgraduate 1 and 2. Okay. Okay. How many are third year students plus the third year? Raise your hands. Okay. Now remember these 4 terms which are very, very common. The common terms are COGI, correlation spectroscopy. It gives only proton coupling, J3 or J4 max, real coupling information it gives. Which proton couples with which other proton. TOCSY is an extended version, total correlation spectroscopy. In fact, 2D spectroscopy is otherwise called correlation spectroscopy. Correlation, how you are correlated with me, him, her and all that. Then the heteronuclear coupling, you remember 2 names, either HSQC or HMQC. HSQC is very common. heteronuclear single quantum correlation, and this is gives you only one bond coupling, while HMBC will give you J2, J3, sometimes J4 between carbon 13 and proton. This is very, very important. And noisy, not noisy, that will give you only space relationship, where the proton groups which are less than 5 angstrom close to each other, in the vicinity of 5 angstrom or less, they will give you space relationship, the dipolar coupling, dipolar aspects. So with this, now see, guys, I am addressing to students. Supposing you are 4 or 5 students are here. Had it been a class and a seminar, I would have brought you. There is no time. Professor Jena will not allow me. Supposing there are 4 or 5 students who are jumbled up in one line, very close, overlapping with one another. I am not able to there, that particular gentleman is not able to see who is there, half is closed. Supposing the resolution is very poor in proton NMR, even if you are giving a high field magnetic field, even if that you find the proton peaks are jumbled up, overlapping in 1D NMR, what you do, you go for the 2D NMR, then what I do, guys, I will push you little bit ahead, push the third little bit ahead, fourth little bit ahead, so that they were overlapping with each other in one line, but now they are separated to form and remain in a diagonal. That becomes the diagonal peak, which is nothing but a well resolved same proton peak. But the important peak I will show you here, that these are the cross peaks. This is the diagonal peak. I have pushed this person, this is the P graph. This is another same proton peak. This is same proton peak. So this is supposing this point is PP, this point is QQ, this point is say RR. So this is nothing but the same, but those which are overlapping, I have taken a very simple one. But supposing there were some overlapping peaks which we cannot decide in proton NMR, they will be shunted here. That will be found here. Even if it is here, its cross peak will be definitely at different parallel positions. Now this is a simple peak. We go for now see this 1.5 peak. This 1.5 peak is J3 coupling with 4.2. Now see 1.5 peak has a cross peak 4.2. Now 4.2 obviously will be coupling with the 4.2 will be obviously coupling with 1.5. So they are almost like mirror images of each other. These are the cross peaks to give you the information. Yes, this is connected to this is connected to this, and this belongs to a different spin system, and this methyl which is at 2 will have no cross peaks, because as you know it will appear as a singlet in 1D, so it does not have a cross peak. This is cozy. Now coming to, and this is one interesting example, where from IR, from 1D NMR, we know that there are 3 methylene protons, 2 methyl groups and 3 methane protons. This is established already from 1D NMR, and IR has revealed it is an ester. But see, these 0.9 peak is misleading. It is overlapping, complex multiplet. Even in 2D cozy, we do not find the 2 diagonal peaks are separated. But you can do that. You can see their corresponding, cross peaks are in a different horizontal parallel rows. So from that, when you go for a tabulation, this is the diagonal peaks and their corresponding cross peaks. This is the table. These are the corresponding cross peaks we found. Supposing we take 4.4, this is the most dishilded higher frequency peak 4 connected to O. Supposing you take 4 peak here. 4 peak is correlated to J3 correlated to 1.5. So definitely we give this 1.5. Then go to 1.5 is correlated to 1.4. We give it to 1.4. 1.4 is correlated to 0.9. So that is found here. Oh, sorry, 1.4 is correlated to 1.3, 1.4. Sorry, 1.4 is correlated to 1.5 obviously, and also to 0.9. Then what happens? We found 0.9 is correlated to 1.4, it is okay, it is understandable. But we find that 0.9 is also correlating with 1.8 and 2.2. Then definitely you will think that these will belong to a different spin system. So we have to go for this arrangement, and we found this methylene protons. These are not methylene protons, these are methene protons. In fact, the 3 methene protons, this is one methene, this is the other methene, and the third methene is here. These are diastereotopic non-equivalent protons giving 2 different peaks with their, the multiplicity cannot be diagnosed with 1D NMR, but their identity can be revealed from the 2D COSY. So that we find 0.9 is not only correlating with 1.4, but also correlating with 1.8 and 2.2 and so on. This, the purpose of telling to you is this: unless you have COSY, you cannot establish the structure without any sheer confusion. You will say that this is the structure, this is COSY. Talking about TOXY is nothing but expanded COSY plus all protons in the same spin system. I will give you this is example. This is an example where you find in the table, in the TOXY table, please keep silence. So I am having some ear problem, so please keep silence. Another 5 minutes, I think I will be finishing. Now this is the TOXY that contains the same information as COSY, J3, real coupling, but other correlations belonging to the same spin system. For example, this, how much? What is E is coming here? 2.35. 2.35 is really coupling with 1.5 D. That will be coming. But in the spin system 1.37, 1.3, 0.8, everything will be coming, and so also in others also everything will be coming. So this will confirm. Without TOXY, total correlation spectroscopy you can manage. It is not a big deal, but further confirmation can be found from TOXY. So also here. Now the most important, we are only 5 minutes away from my last. Now this is, oh, I am so sorry. This is HSQC. I told you this is carbon 13 and proton 1 bond coupling. It does not have any diagonal peak like COSY and TOXY. It does not have a diagonal peak, only cross peaks. And you will find here this is the C13 spectrum and this is the proton spectrum. And any cross peak, any peak, you will find what is the proton value and what is the corresponding carbon value. So to assign the carbon resonances correctly, you have to depend on a HSQC or hetero-COSY. Simply 1 bond coupling, you can assign the carbon resonances. So this has been done. Now coming, this is the most important, particularly for biomolecules, big molecules. If you do not have HMVC, it's not possible. See, this will give you information that this proton is J1 coupling with this one. That will be found in HSQC. But in HMVC, which is heteronuclear multiple bond coherence, that will give you 1, 2, J2, C13 in H, and J3, 1, 2, 3, and also 1, 1, 2, 3. So this and these 3 correlations will be found in HMBC. Even the quaternary carbon, which does not have a proton peak, will be found here as a correlation peak in HMBC. We have done this here. Now see, the 3.7 peak here, 3.7 peak here, 1, 2, 60 will not be found in HMBC. HMBC will not give you any information. COSY and TOXY, they are related, but HMBC and HSQC, they are not related. I mean, in the sense that the HSQC information will not be found. J2, 30 will be found, 1, 2, even the heteroatom is crossed, 1, 2, 3, 60, 59 will be found, 1, 2, 3, 175 will be found. So that will give you, enough confidence in you to establish the structure without any iota of doubt. Now coming to noisy nuclear overhauser effect spectroscopy, where to see this space relationship. For example, this is an amide, N-phenyl acetamide, so which stereoisomer is stable, and the spectra doesn't reveal anything whether this methyl is close to this proton or methyl is away from the proton. The nosy will show that if proton and methyl peaks are close, then you get a nosy correlation peak C. So we found for the proton methyl peak, this, not we, this is not my research. Yes, glycerol story was one of my participation, indirect participation, I didn't do it. He did it, James did it, and I interpreted with him. So methyl has a nosy correlation with 10. This is the amide peak, which is in the downfield position 10, and then 10 peak is also correlated with this 2 peak. So that means the stereoisomer is this, not that. This will not give you any cross peaks other than which are spatially close dipolar coupling alone. And now coming back to the electric vector, I mean the fluorescence. Fluorescence we have already done, and the guys, the Korean guys, I have given. Unfortunately, the abstract I gave under the constant encouragement of Professor Sahu, I gave the abstract, but that didn't, at that time this DTPP didn't occur to my mind. And I saw this while browsing through the literature. I saw a very beautiful and well established molecule DTPP, and then I found, I took all the data, these 1, 1, 1, 1, 1, 2 is here, where is 2? 2 is somewhere, 2, 2, 2, 2, where is 2? 2, 2, 2 is here, 3 is here, 4, 5, where is 6, 7? 6, 6, 6, can you find me 6? 6, where the diastereotopic protons are there, they are not, they have different peaks. And 7, where is 7? Down, 7th, and 8, 9 sitting there, they are non-equivalent. 10, they are equivalent, and 11, coming to 11, where 11, and this is 12, then 13, I am not able to see properly, 13, then 14, 15, 16, and 18, 19, 20. All these assignments have been done. I am not showing you, don't be scared. These HMBC, whatever I told, HSQC, HMBC, COSI, not TOXI. TOXI data is not there, because TOXI is not required that much. COSI and HMBC, HSQC, and noisy data. And I spent about 4-5 hours to really make it a table, and really found that actually the guys are claiming, are they really worth of it, or they are simply saying, I am convinced that the guys have done wonderful work, and I have assigned these positions, both carbon and proton NMR peaks I have assigned, nosy correlations I have also assigned, and the biological applications, ma'am, Haruko ma'am is engaged in some biological research, and this 2OG is naturally present in our cells. It is taking part in citric acid cycle and regulates the amino acid synthesis, ATP production. I will not tell more about this because I am not a biology man. I will commit mistakes, more mistakes than correct things. So, to know the level of 2OG, interestingly 2OG, some cancer cell they have taken out, that is, they call it HeLa cell, they taken out, they extracted and put DIDA, only DIDA, 2OG is there, DIDA, and in situ formation of DTPP, and they took it to the dark room, and then they incident the UV radiation and found wonderful fluorescence, and the intensity of fluorescence that will tell you what is the level of 2OG in that cancer cell, and they can image it, and I will not tell anything more. So, conclusion is 2D NMR can play a very big role in accurately defining the structure with stereo identity of complex molecules, including biomolecules. A simple but tricky molecule like DTPP could be unambiguously characterized by 2D NMR. Along with, of course, I must give a great emphasis to LCMS. The fragmentation patterns have been found. The DIDA pattern and 2OG pattern and the LC purification pattern, and single crystal X-ray diffraction has also been done. And last but not the least, the electric vector and magnetic vector both are horrible vectors. We cannot say NMR is great and fluorescence is not great. So every branch of spectroscopy, may it be electric vector or magnetic vector, they complement each other. They do not compete, but they complement with each other to make the future of organic molecules, the biomolecules, look really properly designed, and the architecture is found out without any doubt. Thank you so much for giving me this opportunity. I don't know, as a school teacher, how much of justice I made to this this talk, which was invited by principal ma'am and Professor Sau, but I did my job. Thank you.
Okay, so since it is already 2 o'clock, and it is and everybody is hungry and everything, so my friend, my younger brother Sudhanshu, we spent long days in Ravenshaw College as faculty, as we are doing PhD with Professor Bashtam Charan Singh, late Professor Bashtam Charan Singh. तेणु सुधांशु बष्टम सार स्मृति रे गोटे गीत गाओ 2 मिनिट्स बष्टम सार स्मृति रे गोटे गीत गाइब जोटा तांकर प्रिय गीत थिला
तांकर प्रिय मो पार थिले तो
हाँ मु कहूची पक्षी
हेलो हेलो
माती
तांकर प्रिय गीत सारंकर प्रिय गीत मो पाकर थिले तो कॉपी
सुनो मु जोटा कहूची पक्षी गाना माती आजी पहाना राती भांगी जीव मो प्रियार मधु तंद्रा मिसा ताती
नहीं सेटा मु
अच्छा
करि परिबिनी किंतु एटा सत भाई से जने एक्सट्रीमली रोमांटिक पर्सन थिले so also we are
any song of your choice
no because he was an extremely romantic person, he was liking all romantic songs. I will be also doing that. Ready? C sharp. कभी मुझको याद करके जो बहेंगे तेरे आंसू, कभी मुझको याद करके जो बहेंगे तेरे आंसू, तो वहीं पे रोक लेंगे उन्हें आके मेरे आंसू। तू जहाँ जहाँ चलेगा मेरा साया साथ होगा। तू जहाँ जहाँ चलेगा मेरा साया, मेरा साया, मेरा साया।
Thank you, sir, for sharing your knowledge with us. We truly appreciate your valuable contribution to this session. We now request Dr. Satyaban Jaina, Dr. Abani Kumar Sahu and Dr. Deepa Nag to felicitate Dr. Sudhanshu Tripathi. We now break for working lunch and would resume a post-lunch session with Dr. Himanshu Shekhar Biswal sir's presentation.